Okay, good morning and welcome to the day 4 of the NSM workshop on HPC for CFD. So this morning I will be giving a talk on what is called as extremely scalable Galerichan methods for modeling continuum mechanics on parallel computers. So this is a talk which is building upon a lot of things that have been discussed previously in this workshop, from the opening lecture to what Professor Somnath Roy talked about, what Professor Mahinder Verma talked about, then Professor Ashok Dey talked about, and then lastly, last night, what Mr. Kuilkar talked to you about the architectures of parallel computers. So see, these are all things which are very important when it comes to parallel computing. So today I'm going to basically give you an idea about scalability. Okay, we have talked about scalability, but also on how numerical methods, the actual numerics, affect things like scalability. So far we have looked at hardware things like, things like memory interconnects, latencies over there, how all those things affect scalability. But today I will talk about how the actual numerical method affects scalability and how this Galerichan family of methods are proving to be extremely scalable. Okay, so the Galerichan family of methods consists of finite element methods, okay, continuous Galerichan methods, discontinuous Galerichan methods, so on and so forth. I'll talk specifically about one method a little bit in detail. I'll cover the other methods a little broadly. It's really hard to do justice to this entire talk, or rather the material that I'm referring to in one hour. So just to give you an idea, I run an entire semester long course on Galerichan methods. Okay, so you can spend an entire semester just about learning this, and people can spend an entire PhD thesis working on this topic. But we'll try to again look at it in a broad perspective, and then once you kind of get the idea of what this method is, excuse me, in the hands-on session, which is going to be more or less like a demo session, we are going to show you a demonstration of a one-dimensional code. We are going to show you how to extract parallelism out of it, right, and show some sort of scaling studies, and to see how to attack a problem, right. Typically what happens is that most people, when they start up, they are handed some code which has been written by some senior PhD student or a researcher or the faculty himself, and it's usually a serial code, and then you try to like kind of parallelize it and extract efficiency out of it for larger and larger problems. So the demo session will be showing you how to actually kind of profile the code, how to parallelize it, so on and so forth. Okay, so it's really the what you say, as they call it, the meat and potatoes of this workshop at this point of time. Okay, so today's talk, I'm going to talk about extremely scalable methods and with a focus on parallel computers for sure. So what is the main motivation for this? The main motivation obviously is large scale complex simulations. So if you look at simulations like this, now this is the simulation of the 2004 Indian Ocean tsunami. Okay, it's a fairly complex calculation. What you really want to compute is the coastal inundation along the coast. How high is the wave when it arrives at the coast? How deep is it going to flood the coast? And what time it is going to arrive, right? So this is a fairly complex calculation. There are lots and lots of uncertainties in this calculation as well, right? Because in the sense that, we typically, when the tsunami-genic event occurs, a tsunami-genic event is usually something like an earthquake or a large landslip into a body of water. You typically have only about a few hours before, depending on where you are, right? So now, for example, in this Indian Ocean tsunami, the earthquake happened in this region over here near Banda Aceh in Indonesia, and it took about a few hours, 6 to 8 hours, for the first waves to hit the coast of India over here, right? So we had about like 8 hours of prep time. Obviously, for people here, it was much shorter. In Banda Aceh, it came in within a few minutes, within the hour itself, and then Thailand within an hour or so. But for any sort of trigger warning system, you need to compute lots and lots of scenarios, because we have a lot of uncertainty on how this tsunami is being generated, right? So what typically people do is that they compute all sorts of scenarios in advance and keep, and then they pick the most probable scenario and say that, okay, this is how it's going to affect it, and then then the disaster management team kind of takes off from there and does whatever they need to do. But to compute all these scenarios requires a lot of computational power, seriously a lot of computational power. Okay, so this is one big thing. Then similarly, related to this is coastal inundation from storm surges and tsunamis. So it's not just tsunamis, it's storm surges as well. So when a cyclone approaches land, when it's about to have landfall, you'll see a surge in the wave height. And once you see this surge wave, it will come and flood, the coast. Especially nowadays, it's a lot more critical with, critical urban infrastructure, which is kind of close to coast. So if you look at even this city, Mumbai, I don't know, a lot of you might have gone down to Marine Drive or other parts of the city, and you can see how close we are to the coast. Fortunately, in the west coast of India, we do not get too many cyclones, but once in a while we do get a cyclone here. And last year there was a cyclone warning. Was it last year or 2 years ago? And the entire city was in sort of a panic, because if the cyclone had made a direct landfall on Mumbai city, the consequences could have been quite disastrous, right? So we need to really understand this phenomenon of basically urban flooding with respect to storm surges. And then obviously that's like from the kind of the weather modeling side. You can look at other complex phenomena like, this is a flow of non-equilibrium, phase change in fuel injectors. This is important in like gasoline engines, petrol engines, aero combustors. Then you can look at fundamental studies like this, like jets and crossflow. But the common overarching theme for this entire set of computations is that they are fairly complex. They require lots and lots of degrees of freedom or lots and lots of computational cells. So they are typically, out of reach from your regular desktop workstations. You cannot typically use a serial code and expect to have computations in a reasonable amount of time. Okay. Now, the tsunami calculations, obviously, because there's so much uncertainty in the initial input, nobody does real-time tsunami calculation. Like if there's an earthquake somewhere, nobody starts a simulation and says that, hey, can I, know where the flooding is. That does not happen with tsunami because of the uncertainty. But when it comes to weather modeling, let's say you're trying to model a cyclone which is coming. There was a cyclone in Bay of Bengal recently. That is a real-time thing, because the moment a cyclone is observed or measured in the Bay of Bengal, the weather simulation guys will start up their simulation code and they'll start trying to predict the path of this cyclone, okay, based on the ambient conditions and the inputs that go into the fluid mechanics model. But now this computation has to be fast enough, because let's say the landfall is going to occur in 3 or 4 days time. The depression has formed somewhere and it's going to take in 3 or 4 days time. But your computation takes 2 weeks. It's useless, right? So if landfall is going to take in about 4 days, hopefully your simulation does not take more than few hours. Why few hours? Because you have to again compute multiple scenarios, because the predicted path of a cyclone can, there's a range it goes through, right? Because that uncertainty covers because the input might be very different. So you have to compute several scenarios very quickly. So few hours you have to compute at least several runs of these simulations. And if you want to do that, then you really need big computing power. And to give you an idea, so let's say that you want to do a weather simulation on this Bay of Bengal region, okay? So from here to here, that's a few thousand kilometers easily, right? And typically the grid size, the ideal grid size that you would like to have is about a kilometer, sometimes even sub-kilometer, okay? And now when you take it to 2 dimensions or 3 dimensions in weather, like you have to take it the atmosphere is about 10 kilometers in height. So you're now talking about billion degrees of freedom here immediately, right? So you need extremely scalable computers for this. Okay. So obviously these are very, very large calculations. We already talked about this in the first lecture. I spoke about ENIAC and we said that it was going to, we were using artillery firing tables and about only 300 floating point operations. So imagine with a billion degrees of freedom and only 300 floating point operations, we're going to get nowhere. But we have these large machines now, right? So we think, okay, now at least these problems have become tractable because now I have machines which are about half an exaflop, or even yesterday some of you went and saw this machine spacetime which is about a petaflop. So we can, these problems become tractable to us in some sense. But there are some fundamental things that we need to ask. Okay, so yeah, this is the other thing that we have seen that there's a big growth towards the exascale computing. This year there will be a debut of an exascale machine in the United States called Frontera. But the questions that I need to ask are current numerical methods scalable? Can I actually use this full computing power which is there? And the second most important question that I need to ask is, are these current numerical methods power efficient? Why power efficient? Because you saw again yesterday the amount of power that is being utilized for these supercomputers, right? So our machine over here uses about 200 kilowatts of energy. We are slated to get more machines and we are kind of budgeting about 3 megawatts of energy right here just for computing resources. The machine here consumes about 30 megawatts of energy. So it's really, really important to see whether even the numerical methods are energy efficient. And what I mean by that, whether numerical methods are energy efficient, we'll get to it a little bit later in my talk. Okay. And obviously the scalability question comes in with Amdahl's law. We have talked about it. Professor Day also talked about it yesterday in his class. So we need to have extremely parallel codes, have very, very less serial portion to the code so that it scales well. Okay. Yesterday you had a very nice demonstration of OpenFOAM. OpenFOAM scales reasonably well for large calculations, but it has some sort of an upper limit because of the way the numerical methods are constructed, not because of the coding efficiency. The coding efficiency obviously will play a little bit of a role. It can be something else can be squeezed out of it. Also the changing hardware, right? So the changing hardware will also kind of push the scalability limits a little bit more. So I'll just spend a little time talking about this plot. So this is what is called as a speed up plot, right? So this yellow line over here, this 45-degree line, yellow line, is ideal speed up in the sense that if I take 10 processors, I should be 10 times faster. If I take 100 processors, I should be 100 times faster. Okay. And you see that the scalability starts dropping after a while, right? So beyond about like 2000 processors, even though I keep increasing my problem size. In yesterday or day before yesterday's demonstration, it was shown that for small problem sizes, you do not get any reasonable speed up. But as you increase the problem size, you start getting better speed up. Okay. So you see, as we keep increasing this problem size from 1 million to about 27 million cells, you start getting better and better speed up, and then but after a certain point it starts dropping. So the maximum scalability that has been observed by these finite volume methods is about like a few thousand processors, few thousand. But now the new machines have millions of processors. So how can I exploit all the millions of processors that could be possibly available to me? Okay, and we need to construct these newer methods for it. A little bit more detail about this plot. Can somebody spot an anomaly here from what has been taught to you? There is one anomaly in this plot. Yeah? I'm sorry? Can you say louder? One plot is going up. That is the ideal line. That is the theoretical line. Theoretical ideal speed up. Beyond? Yes, correct. That's very good. See, you see, it's strange, right? Some of this is going beyond the ideal line. In fact, it is what is called as super linear speed up. Okay. Now, theoretically we have told you that any speed up is going to be below this ideal line, but suddenly now you're seeing things are going above this line. The reason why that happens is that how you are baselining things and how, as yesterday Mr. Koelkar explained, how the different caches are associated with the processor. So what happens is that when you are doing any sort of scaling study, your baseline is the serial code, okay? So let's say you do a 1 million cell case, okay, 1 million cell case, and you got some time for it for a serial bit. But for the 1 million cell case, the entire data will not fit inside the cache. It will be fitting in main memory, okay? But as I keep increasing the processors, okay, let's say I go to 16 processors. When I divide 1 million by 16, suddenly all of it could fit inside cache. The moment that happens, you will start seeing superlinear speed up. Because the cost of going to main memory to fetch your data is no longer there, right? But your baseline still goes to main memory, right? So that is the reason you observe this phenomena called superlinear speed up. So we are not cheating you here. So don't think that we taught you wrong things, by that you can never achieve more than linear. This is an engineering phenomenon. It's because of the way the cache is designed. Now, if all the machines had uniform access time to memory, like there was only one level of memory, no different caches and all that, just main memory, then you will never get this superlinear speed up phenomena. It's only because you have different levels of hierarchy of memories and things start fitting into cache, you will start seeing this superlinear speed up, okay? But irrespective of this, what is going to happen is that you are going to have an upper limit. Now, every method will have this upper limit. Remember, because every method is going to have some sort of serial portion. No method is perfectly embarrassingly parallel. Our main aim is to reduce this serial portion. Okay, and that's what we are going to focus here. Now, the class of methods that I'm going to talk to you today about have much lesser, serial component, hence they scale better. They also have an upper limit at some point of time, okay? It's just that that upper limit is so far off right now that we can scale on current machines. Okay, now let's switch to the method. So now we are talking about trying to solve these large problems, and I am going to now make this classification of all these element-based Galerichan methods. Now these element-based Galerichan methods, what they do is essentially whatever PDE that you want to solve. See, remember, any natural phenomena or any phenomena that you want to observe in our language is described by using a partial differential equation, okay? And the idea is that I want to solve this partial differential equation on some sort of a computational domain. Typically, this computational domain is in space, okay? And we are trying to solve it in some sort of maybe 2-dimensional, 3-dimensional space, depending on, whatever the problem may be, okay? And what do? We kind of take this computational domain and we discretize it. The word is discretize, right? We separate it into smaller and smaller computational domains, okay? And then we apply some numerical technique. Now, what are the different types of numerical techniques that are there? There's finite element, there is spectral elements, finite volume, discontinuous Galerichan, so on and so forth. And let us understand what is the fundamental difference between these two, okay? And how do I sort it is that you have one thing called as the continuous set of methods and the other is called as the discontinuous set of methods, okay? So what do I understand by continuous and discontinuous set of methods? So in the continuous set of methods, the phenomena that I'm looking out for in some continuum mechanics problem is usually smooth in the sense that there is what is called as C0 continuity in your solution, okay? There are cases where there is no C0 continuity solution. What is the case? We talked about a case yesterday where there was no C0 continuity. We even solved a problem based on that. Shocks do not have C0 continuity, right? Okay. But for a large class of problems, there is C0 continuity in your solution, okay? So if your numerical solution provides C0 continuity, then you are in the continuous spectrum. If your numerical method allows for discontinuities, then you are not zero. The solution, you can apply this discontinuous to continuous problem, right? I can use the finite volume method to solve something which is continuous. We have done that all the time, okay? But the finite volume method is also useful for solving shocks, which is on natural discontinuity, right? So the discontinuous set of methods allow you to solve for discontinuities, but in continuous schemes, you have to have continuity in your solution. Otherwise, you will not be able to get to the correct solution, okay? Then the further distinction is what is I call as on the h axis and the p axis of approximation. So h is the number of computational elements that you have, okay, and p would be the polynomial order of approximation within the element. Remember, we are always trying to approximate a solution, right? We do not have the exact solution to the PDE that is there, right? So we are putting in some sort of approximation, and this approximate solution comes in some sort of polynomial. Some polynomial representation is there, okay? Now, when I take this computational domain, I have two options. I can fill it with large number of elements, like discretize it large number of elements, but keep the polynomial order of approximation within the element small, like low p but more h, okay? More elements but lower order of polynomials approximating the solution. The other option for me would be to have fewer elements but have higher orders of polynomials representing the solution within the elements, okay? So when I classify it in that way, finite elements are nothing but, first of all, they are on the continuous spectrum. They use low orders of polynomials to represent the solution, and you use large number of elements. On the discontinuous side, you have the finite volume method, which also uses low orders of polynomial. What is the order of polynomial in finite volume? Yesterday, what order of polynomial would we using? No, I'm talking about polynomial representation. I'm not talking about the order, the numerical order of accuracy of computing fluxes. I'm not talking about that. Let me ask you, inside whether you used a staggered grid or a collocated grid, your variables of interest, which could be something like pressure, velocity, etc., how many values did it have within a cell? 1. So essentially one value represents the entire cell. So it's essentially a zeroth order polynomial, right? If it is a first order polynomial, there should be minimally 2 values to have some sort of a linear representation. 3 will be quadratic, 4 will be cubic, so on and so forth. So it's essentially zeroth order in terms of polynomial. But because I have zeroth order in terms of polynomial representation, to get an accurate solution, I need to have more h, right? So that's on the discontinuous side. On finite elements, typically you have lower orders. You must have heard about linear elements. The shape functions that you talk about in finite elements, right? The shape functions, they basically are representing this orders of polynomial accuracy. So typically you have bilinear, linear, so on and so forth. But I can keep increasing this order of polynomial, okay? If I do that for the same, remember again, as engineers in some sort, we always want to get a solution with a certain accuracy, with a certain amount of representation, right? So I can increase the polynomial order, but reduce my element size, okay? So when I do that on the continuous side, I get to what is called as spectral elements, which Professor Verma talked about, okay? And on the discontinuous side, where I allow for discontinuities in the solution, I get to something called as discontinuous Galerichan, okay? Where even though within an element, because of the polynomial representation, the solution is continuous, across elements, I allow for discontinuities, okay? So within an element, I have to have a continuous solution because that's how I'm representing it using some higher order polynomial. But across elements, I will have a discontinuity. And then I can look at the absolute extreme case where I have only one element, which is the entire domain, and an arbitrary high order representation in polynomial. So that's essentially spectral transform, right? So if I go to the spectral transform where I'm looking everything in the, the wave space, so I am just then looking at the spectral transform, okay? I'm talking about solution discontinuities. So when you're talking about solution discontinuities, the advantage that is there is that it can represent physical discontinuities. Like physical discontinuities in natural phenomena like shocks, or for example, if you were to look at it from a solid mechanics problem like cracks. Cracks in a material are basically discontinuities. Those can be modeled only if you have some sort of numerical method which allows for this C0 discontinuity. Otherwise, your solution will, if it is C0 continuous, then you cannot, use this. Okay. Oh, okay. I seem to have lost my connection here. Anyway, fine. I'll switch to here. So I hope this is clear. So we will now then talk about the discontinuous Galerkin method. But before that, let's see what do we really do. So typically we have some sort of canonical equation, okay, some sort of PD that which has a temporal derivative component, has a spatial derivative component. Now I'm just showing it to you in one dimension of x, but this can be arbitrarily extended to any number of dimensions. Okay, so you have a variable q which is a function of space and time. Okay, and f is also a function of space and time, and f itself is a function of q. What do we do when we want to solve this canonical equation? First, we approximate our solution variable. Okay, so we approximate the solution variable using this basis functions. Okay, so this is expressed as a summation of about n basis functions over here. Okay, where psi are the basis functions and n is now the order of the polynomial. Okay, so if I want a first order representation, then I will choose two polynomials 0 and 1. If I want second order 0, 1, 2, so on and so forth. Okay, old style C style indexing, so I'm starting from 0. I can like label it as 1 and then change it around, but this I'm starting the numbering from 0. Okay, so q is then the expansion coefficients, psi are the basis functions, and obviously as I said n is the order polynomial. You can pick whatever n that you would like to choose depending on the level of accuracy that you want. Okay, what do? I substitute this approximation. Okay, I have approximated my polynomial qn, but the moment I substitute that approximation, this canonical equation partial of q with respect to t and partial of f with respect to x is no longer going to be satisfied. I'm going to get a residual, right? Because q is an approximation, q is not the exact value. Okay, so I now have some sort of a finite dimensional approximation, and I need to resolve this error, right? This residual error that is coming. So I do it in a weighted sense. So what I do is I multiply this approximation with a test function and I integrate it over the computational element, not over the whole computational domain, but just over the computational element, and I drive that residual to 0, right? So if I multiply it with a test function, another test function psi, okay, which is of the form of the same basis function. Okay, the form of this test function is similar to that of the basis function. Okay, and then I multiply it and I drive it integrally. So this is basically what you call of the weighted residual method, right? So I am in a weighted sense, what I am doing is that at any point within the element, when I substitute qn, I am always going to get a residual r. Okay, I am always going to get a residual r. There is going to be an error, there is no doubt about it. We always commit some numerical crime. But in a weighted sense, over the small computational element, I am driving the sum total of all the residuals to 0. Okay, in a weighted sense, I am driving the sum total of all residuals to 0, and that's what this last thing is saying. Okay, all right. So then I obviously the domain is obviously partition. I'm just giving an example of a one-dimensional problem where you have maybe 4 elements, but this can be expanded to any number of higher dimensions. Okay, so as I said, the integral of the last term with this of this residual is essentially orthogonal. So that's the reason why that will be driven to 0. So if you look at your solution vector, which is q of xt, and then you have the approximation, which is qn, the residual is orthogonal to the solution qn. So that's the reason why this will kind of get driven to 0. Okay. Now, from here on, we start using things that we learn in calculus, right? So we take this weak integral form, okay, we take this weak integral system and we integrate the second term, okay, and then we get this square bracket, which is basically the evaluation of this function at the boundary gamma for every element, okay. Now the reason why we do this is where now we are slowly drifting into what is called as a discontinuous Galerkin method, okay. Now in the discontinuous Galerkin method, this term becomes important. If I were to go into the finite element variation or the continuous Galerkin formulation, since there is C0 continuity, the boundary terms have to be exactly the same. There can be no discontinuity, there can be no jump, okay. So this boundary term, when I look at it from a computational domain, the entire assembly of equation sense, this will vanish, the boundary terms will vanish. But in the discontinuous Galerkin, if I have to capture something which is discontinuous like a shock, this jump term will exist, okay. So if you look at it, you see I can have a solution such that my left side element and my right side element are discontinuous. This is what enables me to capture shocks. So I have a discontinuity over here, okay, and that is where in this gamma E term, that's where this is incorporated, okay. So how do I allow this gamma E term to communicate, okay, and this comes back a little bit to finite volume theory, okay. So the way we do this is we use what is called as a Riemann solver or a numerical flux, and you have studied a lot of these schemes. Yesterday also some schemes were discussed. The standard upwinding type of schemes, central differencing schemes. All of this can be applied to how to compute this F star, which is that jump condition. It all depends on the nature of the problem. Now, if you have a problem which has strongly directed flows, okay, then you will use some sort of upwinding scheme, okay. If you have something which is more elliptic, then you will start using a central kind of a scheme where the information comes from both sides, okay. How you compute this numerical flux depends on the nature of the problem that you're trying to solve, okay. And this F star is the way you are able to communicate between neighboring elements. This is how the solution information spreads, okay, in this scheme. Now, if it were in the finite element technique, if it were in the continuous Galerkin technique, this F star does not exist. You would just have one continuous solution. You will not see this jump, okay. And I'll tell you the advantage discontinuous Galerkin gives in a minute in a slide, okay. So as I said, you can use standard Riemann solvers. So this is an example of the Ruzanov flux, or also known as a local Lax-Friedrichs flux. So which has a dissipative component and also an upwinding component which allows you to do the communication, okay. I cannot spend time on Riemann solvers too much in this lecture because Riemann solvers itself is a PhD thesis topic, okay. People have written dissertations on Riemann solvers itself. But the basic idea is that all the rich schemes that you have which have been developed, any of those can be applied over here in this framework, okay. Now, what sort of basis functions do I use? Remember, within the elements, I'm approximating the solution using some basis functions. Typically, we use Lagrange polynomials or cardinal functions, okay. Now, what are cardinal functions? Cardinal functions are functions such that at the internal degrees of freedom of these elements, they are either 1 or 0. Like they are 0 in all other places except for one point where they are 1. There's obviously variation in between, okay, and those are essentially known as cardinal functions. Now, I'm showing you cardinal functions for first order, second order and third order for triangular elements, and you can see how the solution varies. So, for example, you can see in n is equal to 1, there will be 3 degrees of freedom when you go to a triangular element, which will be the 3 vertices of the triangle, okay. And you can see this function is 1 over here and it is 0 on the other 2 vertices. Similarly, it is the second basis function is 1 on the second vertex but 0 on the first and third vertex, and similarly The third basis function is 1 on the third vertex but 0 on the second and first vertex. So these are essentially called cardinal functions. You can construct cardinal functions for higher orders, n is equal to 2, n is equal to 3, so on and so forth. You can construct it to arbitrarily higher orders. Okay, it's very easy to construct these cardinal functions if for regular shapes like quadrilaterals, triangles, etc. It becomes a little harder to construct it as your shapes become a little bit complicated. Like, by the way, this can be extended to 3 dimensions easily as well. All you need to do is take what is called as a tensor product. If I take a tensor product of this basis function in the third direction, then I'll get 3 dimensions. I can take a tensor product in the 4th dimension, like if there's a 4th dimension of space that you want to investigate or so on and so forth, okay? But you can keep taking tensor products and keep building these cardinal functions or basis functions. But if you start going to arbitrary polyhedra, it becomes a little bit hard to construct these functions, but people are working on that, okay? Okay, now I apply this to the constitutive equations. Now the constitutive equations could have, source terms as well, so that's why you have this new Sn. And as I said clearly that f star is the numerical flux, okay? And once I put the polynomial approximation on an element by element basis, what happens is that I can now do this small tiny integral, okay? And I can start defining these tiny integrals as, this will be essentially what is called as the mass matrix, okay? So I define the mass matrix, I have the flux matrix, and I have the differentiation matrix. So I keep defining these small integrals as these mass matrix, flux matrix, and differentiation matrices, okay? And when I put this into the semi-discrete form of the equation, okay, and I pre-multiply by the inverse of this mass matrix, okay, so I can then come up with this final equation over here, okay. So the good part about this scheme is that this mass matrix, the dimension, because this is being constructed on an element by element basis, this depends on the order of your accuracy, okay. Now going back to this basis function example, my first order approximation has 3 vertices, okay. So my mass matrix is actually 3 by 3. My second order is 6 basis functions, so 6 degrees of freedom within the element. So my mass matrix is 6 by 6. The last one is 10, it's 10 by 10, okay. Now I have to invert these matrices, right? Inverting a 10 by 10 matrix is trivial, and you need to do this only once, okay. Obviously then the next question that you will ask me is that all these elements, whether they are triangles, will not be of the same shape, okay. But you can do a conformal mapping. I can compute the Jacobian and multiply this mass matrices with the Jacobian to get to the correct shape from an idealized shape, okay. I hope everybody here knows what a Jacobian is. You can take any, say for example, a equilateral triangle, and I can make it look like a scalene triangle by just multiplying it with a Jacobian, right? I can just distort that equilateral triangle. And similarly, I can take that scalene triangle, multiplied by the inverse Jacobian, and get back the equilateral triangle. Everybody understands this. So I just need to know the Jacobians, okay? And if I use the same kind of elements in the entire mesh, which we typically do, it's not that it's not uncommon to use different kinds of elements, but most calculations we either stick to only tetrahedra or only hexahedra or things of that sort. I can then reduce the problem very, very quickly, okay. So to basically just matrix vector multiplication, right? Multiply the Jacobian, do a matrix vector multiply, and I just have to do the last equation. I will just go about doing matrix vector multiplication if I am to solve a time dependent problem. Now if it's a steady state problem, I then will have a global assembly of equations and have to solve it in an iterative manner. But most transient problems, I can then just put it down to kind of matrix vector multiplies, okay. The moment I cast my problem as simple matrix vector multiplies, my computational life becomes very easy, okay. So what happens is that you can then split it up into different things. You can look at it as a flux integration method, a volume integration method. I can then choose to kind of, like we talked about accelerators yesterday, I can choose to offload each of these operations, these matrix vector operations onto graphic cards or any other sort of accelerators. And since you're doing this on an element by element basis, this is almost embarrassingly parallel. It is not really embarrassingly parallel, it is almost embarrassingly parallel, because each of these matrix vector products is independent of what is happening in the neighboring element, except for computing that Riemann flux, where that Riemann flux is a slightly serial part, because I have to now talk to the neighbor. Yeah. So just going back a little bit, so your typical finite volume stencil, right? It looks like this. Remember, finite volume method is a zeroth order method. You have information of within a cell of only one quantity, right? Now, if I want to compute something with a higher order of accuracy, what do? I have to enlarge this. So if I have to compute with a second order accuracy, I have to take information from the neighboring 4 points. If I want to go with fourth order of accuracy, I have to enlarge this stencil and I have to keep taking information from more and more points. Now, the moment this point, if it sits on, say, a CPU boundary when you're doing a parallel computation, the amount of information I need from my neighboring nodes, volume increases. And remember what Professor Verma said, communication is the one that will kill you, right? You'll have to communicate larger and larger of information. So typically what happens with traditional methods is that if you want a higher order of accuracy, which automatically means a higher fidelity of simulation, I need more information coming from my neighboring processors, and that will kill my scalability. Okay? And most of these methods suffer. That open form scaling I showed you, it does not scale beyond those 2000, 3000 processors because of this issue. Because the more information I need, it has to come from my neighbors, I can't scale them. So this is a fundamental issue in the numerics of the method. Okay, so if you look at the so-called sparsity pattern, how a sparsity pattern basically shows in a matrix form how you're communicating with your neighbors, right? So this is a typical sparsity pattern for a finite volume mesh. Okay, you can do some clever reordering, you can improve it using algorithms as the reverse Cuttle-Mekki algorithm and reduce the so-called bandwidth of this matrix to improve your calculation. But still it does not really improve a lot. Whereas if you look at the sparsity pattern of the DG method, you will see that it is fairly dense and it's very banded like this. Okay, it's really, the bandwidth is extremely narrow. And as I keep increasing higher orders of accuracy, all that is going to happen is that this part is going to become wider, but you're not going to have too much sparseness. So this is the real power of this class of methods. And you can see that once we offload things onto GPU, this is some test we did on a GPU without even optimizing for the size of memory that is coming into the GPU, fetching from memory. And yet with higher polynomial orders, we were getting roughly about 8 times speed up. When a student of mine, master student of mine, she optimized it for memory fetches and filling the caches properly. She did all that. We nearly got 25 times speed up when we had to optimize it for, say, a fourth order polynomial. Okay. The other question is the scalability. Right. Remember, I showed you the first plot where OpenFOAM didn't scale beyond about like 3000 processors or something. Mind you, 3000 processors is significant. Okay. I mean, you can solve most engineering problems in that. Okay. But what I'm talking about is like these next generation of problems that are coming where you need millions of processors, okay, or hundreds of thousands of at least. So this is a scaling study we did with fourth order discontinuous Galerichan method and also fourth order continuous Galerichan method, and you can see that we have like pretty much linear scale up till about in this case about 8000 processors, and then it starts dropping, right, because this is a lower order. Now the moment I increase the order of accuracy, go to 8th order of accuracy, I see nearly linear speed up all the way up to 32,000 processors. Can you tell me why it didn't go beyond 32,000 processors? It's just because I did not have that many processors. The machine had only 32,000 processors and I used up the entire machine. But if somebody can give me a machine which has more than that, I'll try to do the scaling study and prove it to you that this thing will scale even beyond that. Okay. So after I left, so Giraldo is my postdoctoral advisor. After I left that group, they have shown scalability on this for this particular method up to I think about 5 lakh processors. Okay. So and the jury is still out there of how much you can scale. Okay. So clearly this class of methods are able to scale to larger and larger number of processors. So that means that you can solve larger and larger problems for sure. Okay. And this code was targeted towards a weather modeling code. Remember our original slide, we talked about looking at modeling storms, etc. Right? So there, easily if you want to go to a 100-meter resolution scale, and let's say that you want to simulate the area of something like Bay of Bengal, you can clearly understand, how many degrees of freedom that you need. So you can do you can do the arithmetic, and it's quite large. Okay. The other thing that we are really interested as engineers is error, right? Finally, the question that I want to answer is that I know that whenever I do a numerical simulation, I'm committing a crime. There is an error. My goal is that how much error can be tolerated and how soon I can get to that error level. See, when you're doing, say, lift over a wing, okay, we can never get it 100% accurate. We can never get it 100% accurate. But we can say, okay, it is plus or minus 1% or plus or minus 0.01%. My question is, how much does it cost to get to plus or minus 1% or how much does it cost to get plus or minus 0.1%? Because that's what, as an engineer, we need to ask. Okay. So we typically define error in terms of norms. So if you look at L2 norms, the question is, how many floating point operations do I need to do to get to a specified level of error or specified acceptable error? That's the question that I need to ask. Okay. Obviously, that level of error cannot be below machine precision. Remember, errors are of different kinds. There is error in the numerical method, the higher order terms that you disregard in your Taylor series expansions. But once that happens, there's also an error in your compute, right? Because your number that is going into your computer is only represented by a certain finite amount of bits. So the least significant bits keep getting thrown out. So the digits beyond your decimal point, it doesn't keep on going to infinity. After a point, you truncate it, right? So that's called truncation error in some sense. Sorry, machine error. Truncation error is the Taylor series expansion. Point is the error, let's say that my acceptable level of error is 1e minus 3, which is higher than machine precision, right? I can always drive everything to machine precision. But let's say my acceptable error is 1e minus 3. Question is, how many floating point operations do I need to do to get to that level of error? Okay. And what we have done here is we have compared the finite difference third order method with different orders of method of DG, and you can clearly see this axis, the x-axis is on a log scale. Okay. So you can see that we literally require one order of floating point operations less compared to finite difference methods to get to a specified level of error. Now this is really, really important. That means if I'm using less floating point operations to get to a specified level of error, that means I'm getting to my solution faster, right? I'm getting to my solution faster. It also means another important thing. It is the energy that I consume, right? It is the energy that I consume. Remember, less floating point operation means less time on the computer. That means less electricity that I consume. Also, there's another factor which comes in because you saw the sparsity pattern. That means the method is fairly compact. That means all the data that is required for you to do the computation is close to each other in memory. That means I do not have to go to higher levels of memory often to get other chunks of data. So that means if my memory is far more local, that means fewer number of cycles wasted, fewer number of page faults to go and get the data from there. That also contributes to lower energy consumption. We actually measured the energy. So there's an energy meter that you can tack on to your CPU. Your OS provides that. And you can figure out how many joules you used for a computation. And when you compare the third order finite difference method and a third order DG method, you can say that, clearly see that for a specified level of error, the amount of energy that is consumed by the DG method is an order of magnitude less, right? So not only do we get solutions faster for the same accuracy. So there are two things that you have to compare, right? For the same accuracy, can I get to a solution faster and can I get to a solution cheaper? That's what this is telling me. Okay, so to conclude this talk, what I'm trying to say is that obviously to solve more and more complex equations or more and more complex phenomena, we need larger and larger computing power. Like especially if you go into multiphysics, right? You're trying to do fluid structure interaction or you're trying to do chemical reaction. The number of equations that you need to solve, the number of degrees of freedom that you need becomes larger and larger. So the amount of computing power that you require is obviously going to go high. But what also is important is whether you're able to scale. I might have, you know, a 1 petaflop machine, but it is useless if I cannot scale it, if I cannot scale my problem to more than 20 nodes or like 50 nodes, then it becomes useless. I need a method that actually scales, okay? And obviously, very established techniques like finite difference, finite volumes, they have their limits to the scalability. So we have to really start thinking on these newer methods which will scale, okay? And DG is one of the methods which shows promise. There are other methods as well. It's not that DG is the only method, but DG is one of the methods, or Galerkin-based methods is one of the methods. Element-based Galerkin methods is the one which shows some reasonable promise to scale to hundreds of thousands of processors. The other thing is power efficiency, right? We showed that it consumes less energy to get to the solution for the same accuracy and less time. And lastly, this is the most critical point. In the past, when things like ENIAC was built, they had the numerical method in mind, they had the calculation and application in mind, and then they built the computer based on that, right? So they designed the machine for the application of whatever it was. Today it's the reverse. The electrical engineers do not come and ask applied mathematicians and mechanical engineers, hey, what sort of processor would you like to design? They design general processors. It's driven by different forces. Whatever electrical engineers design, based on whatever engineering limits that they have, we have to adapt our computational methods to those processors. And you can see this evolution in terms of the GPU technology. GPUs were first made for gamers, right? It was a gaming market which gave the GPU. Then suddenly some set of people realized, hey, what the gamers are doing is essentially looking at that video tile and just doing some arithmetic on that RGB, and our computations look similar. Can we adapt that to doing scientific computation? That's where the origin of GPU computing started, okay? Even today, the largest market for computers is still not HPC. It cannot be HPC, right? I mean, we are a small community. It is very important. It's a very important and addressable market. But the biggest market for whatever commercial processors is public consumption outside. Your cell phones, your average desktops, your gaming consoles, that's what they're really going to design processors for, okay? And once they design things so that, we have to then look at our numerical method and say, okay, can I exploit that in some sense to use it? So you have to use a general purpose processor for your specialized computing. So you have to keep in mind about your numerics, okay? So with that, I think, wow, I finished bang on at 11 o'clock. We have a few minutes for questions. Yes, if there was a mic somewhere, can you just, get it, pass it on.
So why solve a hyperbolic equation? That means we go high order for adapting ENO and VNO category equations, okay? And as you shown, Galerkin method also doing a high order thing.
Yeah.
So how can we compare that, because VNO is there, then next family's TNO algorithms are there. How can we compare with DG methods?
Yeah, so that's what I'm saying. So let's go back to this plot. Yeah, this one. So if I took VNO or ENO over here, right? For VNO and ENO, I would need more information, right? Let's say I take a 7th order VNO method or something like that, okay? So I need information from all the way here. Now it will give you reasonable order of accuracy, but from a computing perspective, what starts happening is that I need more and more information from my neighbors, right? So I need information from a lot more neighboring cells. Now if I'm in the unfortunate business, like if I'm an unfortunate cell that I'm lying on a CPU boundary, where my neighbors are in another node, so now I have to communicate, I have to request for that information through an MPI send and an MPI receive. So that adds a lot of computational cost, right? But if in DG I want to go to a 7th order accurate method, I do not do all that. All I do is that this approximation, this n, which is locally inside the element, I make it 7th order. And once I do that, that information is always, for every element, the data is within that CPU only. It will never go to the boundary. So you will never have that issue.
It is much preferable over ENO and VINO.
It is much more preferable in terms of ENO and ENO from a compute perspective. Let me put some disclaimer over there, okay? I'm not saying VINO and ENO are completely useless or whatever it is. I'm not saying that. I'm just saying that from a computational perspective, this is much better. But this has its issues in some sense. But the moment I put it 7th order here, I have to ensure that my solution within this 7th order cell is C0 continuous. Whereas VINO and ENO will allow discontinuities along that entire 7th order. So there are some caveats to this.
You said sharp interface problem. Okay.
Yes.
Like
so what will happen with this kind of method is that when you have strong shocks, or let's say I'm trying to advect a square wave, and now the front of the square wave is in middle of an element. The middle of an element is now being represented by continuous polynomials. So you will start seeing these Gibbs oscillations. Okay. So once you start seeing these Gibbs oscillations, trying to force a sharp discontinuity with a continuous polynomial, you'll start seeing oscillations, you'll start seeing ringing at the high and the low level. Then you have to do something called as filtering, etc., to get some noise-free solution. So you have to do some after treatment. So there are techniques to do that.
I mean, we have to make balance between from the perspective of the computing power and efficiency.
Yes, we have to make that balance. That is true. The question is that, what am I trying to solve? Now, if I'm looking at some really fundamental methods and I'm just looking at propagation of square waves and things like that, I mean, you can do some studies using DG. But the point is, if I want to solve a large problem like weather, right, and I want that scalability, I want to go to 1,000,000 cores, right? So then I have to use a method like this. Yes. I think if you ask the question in this, it would be better.
So, anybody has explored use of this technique for WRF, because that is one of the popular models.
I'll tell you what WRF is. WRF is basically a collection of different codes, or rather different models, which is used for weather prediction. Okay, and when you're looking at a weather prediction code, there are different layers to it. There is one thing which is called as the dynamical core. Okay, the dynamical core essentially dictates the fluid mechanics of the atmosphere, which is our basic Navier-Stokes equation. Okay, on top of it, because you cannot resolve everything, right? You cannot resolve clouds. You cannot, because I said, our current state of the art is that each cell, if you're trying to solve the Bay of Bengal, each cell is about 1 kilometer wide. But your clouds are much smaller than that. So you cannot resolve the clouds. You cannot resolve rain, for example, right? So all those things come in form of what is called as subgrid scale models. So WRF is built on top of that. There are lots and lots of models for rain, for clouds, so on and so forth. But the essential dynamical core of WRF today is a finite volume based method. Okay? I think it's finite volume or finite difference. But there are groups who have converted the dynamical core into DG. Okay? In fact, there are different weather codes, some of which it's not public. There is a US Navy code called NUOPSI, which actually has the dynamical core built on this technique, which is based on DG. WRF is also moving towards that. They have tested it. But the more, what you say, I don't want to use the word commercial, production runs are done still using the older technique. Okay. Yeah, people are actively working on it. Yeah, give them.
Also, you said processor boundary, we need information from the other processor as well. Okay.
Yeah.
So in that case, DG proves much better than other techniques. Okay. So same is true for physical boundary.
No, physical boundary does not have much effect, right? The physical boundary is, you mean like computational domain physical boundary,
Yes,
right?
sir.
No, I don't think, you mean to say in application of boundary conditions,
Because
etc.
when we know take, we need information of 7 point. Then we
Oh, you mean the ghost cells and other things? That does not purchase any big computational efficiency. There it's the same numeric technique. I don't think any great computational advantage comes out over there. Yeah. Yeah, Professor Day, yeah, so ask a question. Can you just... Yeah, but for the online people.
Yeah, I mean, for that physical boundary, whenever you go to the physical boundary, any numerical methods except the DZ or PSPG or something like that, or spectral, you lose your order of accuracy.
Yeah.
And that is numerically also consistent. You can prove that mathematically. If your central scheme is, let's say, XYZ order of accuracy, always in the physical boundary, you go down 1 or 2 order less because it has to be one-sided. So that is one point. And second point, if you add to that we know and ENO. So this is where I think his talk is so nice to complement my yesterday's talk, in the sense I have been talking about structured, non-structured. So even in finite volume, the block structured solver is much more preferred if you want to use the going towards the Exascale computing and things like that. So what happens then? See, there are a lot of other things probably we can't talk here. Your how you parallelize your code. You have to use both the shared memory and the communication amongst the processors. So you try to reduce that. How you say another thing, all these methods which has the domain decomposition. That is very, very important, because how you do the domain decomposition, it's going to share the load, and that bandwidth what he has shown, that's going to make a lot of difference.
Yeah, so going back to...
Yeah, that picture is a really nice one, which gives you an idea how you should program things actually. It can be really spread, and you can narrow it down and then make a band. I think I talked about that book. If you look at that iterative methods book by Yusuf sir, it shows this block structure, different kind of iterative solvers, how it behaves. So there are a lot of other things also. Numerical methods are probably in the top level they're sitting, but then there are underlying things which you have to also take into consideration. So block boundaries are always a problem, but there are ways to handle that. But still, interprocessor communication should not be the killer of computing.
Thank you. Any other questions? Yeah.
Sir, can you talk about application of these methods in perspective of acoustics, especially underwater?
Okay, from a perspective, I'm not an aeroacoustics expert and definitely not an underwater expert, but point is, if you look at, trying to solve things in terms of underwater, first of all, you have a much larger speed of sound underwater, right? So, you are mostly in the incompressible region most of the time over there, but there is possibility of shock waves over there, right? You can use these methods to solve it as well. I'm trying to think what would make it any different. I don't see any particular difference. The way I look at it is just I look at it as a PD, and I'm able to solve the PD in a scalable way. I think Professor Dey wants to add something to it.
It's already there. Nectar++ used the HP spectral method,
Correct, yeah.
and which we are using for acoustic solution. So it does.
Yeah. Acoustics for me is another PD. I just look at it as a PD and I look at how to solve it. That's it.
So one more question, sir. Sir, there is one paper which I am looking right now. It's a conference paper, but they use machine learning methods. So they claim to have a speed up of 292 times compared to a GPU using a lattice Boltzmann method.
Okay.
For a particular case. So they used a deep neural network to predict the results, and accuracies are also pretty much good. So, uh, does this, combining this with FEM will give a better accuracy?
Combining that deep learning with
Yes,
FEM or
yes, as an initial condition.
okay, so the way I look at these machine learning problems in CFT, applied to CFT, and look at continuum traditional numerical methods, is that what I like to call what we do as the forward problem, right? We are using something to predict something. Machine learning does the different thing. It has a large data set and it is doing the inverse problem. So somebody has to generate these large data sets, right? So if I go back to the tsunami problem, right, I mentioned that you do not know the source of the tsunami. There's a lot of uncertainty around it. Okay, so you do a lot of probabilistic calculations. You do a lot of scenarios. Now let's say I do 1,000 data points, but those 1,000 data points have to be done by a forward method, whether it is finite volume, whether it is DG, I don't care. I have to do 1,000 calculations, have that data points ready. Then the machine learning algorithm can take that information from the data and then reverse compute for any particular scenario. So your question is it better to use FEM or is it better to use DG? That is irrespective, right? In the sense that for that forward calculation, if FEM is more efficient and going to give you 1,000 calculations with good accuracy fast, FEM. If it is DG, it is DG, right? Machine learning is only going to do the reverse for you. That's all there is to it. So remember, anybody who has taken a class in statistics and probability, everybody understands that any extrapolation is fraught with a lot of risk. Interpolations are good, extrapolations are bad, and machine learning does extrapolation, and I'm sometimes worried about it. That's all I have to say.
But many times it is proved that they solve the physical equation. Sometimes based on the loss function, they are seem to have.
If you compare machine learning to something like what Professor Dey talked yesterday, what Professor Somnath and Professor Mahendra talked, and what I'm talking, we are taking the real governing physical equations. When you write down a governing equation like Navier-Stokes, there also you're committing a crime. You're idealizing, you're assuming continuum and all of that. But this is the closest that you can get to the real physics of the problem. Yeah. Machine learning is about data. It's like, saying in Mumbai, the last 10 days, we have had 30, 31, 32, 33, 34, and then tomorrow it's going to be 32. But suddenly, if there's some wavefront from physics coming and, a cold front comes, we don't know. Machine learning cannot predict that. Unless it's taking information from the cold front as well. But remember that data set is as I said, it's an extrapolation. And extrapolation is always tough. That's my personal feeling. I know machine learning enthusiasts get very upset when I say that, but I don't want to get into that controversy. Professor Dey is laughing at the end over there and he's waving his hands. But I hope, there is some...
Actually, then the time you spend in generating that data, whatever methods you use, that's huge. Otherwise, most of the physical problems that we have been talking, they are non-linear in nature.
Yeah.
So to map that non-linearly using your data set and train your neural network, it requires a lot of effort. And by that time, you analyze the data and get your actual physics actually. Why do I invest my time there?
So I would like to just end by quoting one of my colleagues, Professor Borkar from electrical engineering here. He says, you show a machine learning algorithm an image of a cow and it immediately recognizes it as a cow in a farm. The reason is because you have shown the machine learning algorithm thousands of images of cows in a farm. Suddenly you show the machine learning image, the photo of a cow tied to a boat on a beach, it's going to recognize it as a dog because it's never seen a cow at the beach. So I hope you're getting what I'm trying to say. Something crazy happens, the machine learning algorithm is just going to fail. But this is slightly more grounded in physics. But that's our philosophy. Anyway. Okay. Yeah. There's an online question. Okay. So is this Galerichan method used for large eddy simulations like supersonic turbulent flow? Yes, discontinuous Galerichan methods can be used for large eddy simulations. You just have to take the Navier-Stokes equation, put the LES closures, it can be used. Any canonical PD, yes, definitely it can be done. Thank you. Yeah. Okay, we'll take a short break and we'll come back for the hands-on session. Thank you.
So, good morning. So, let's start with the second session. So, what we are going to do is like we have a very simple 1D advection code for discontinuous Gaussian method, right? So, idea is we have a Gaussian and we will just like advect it, right? And we have a periodic boundary condition. So, essentially after one round it will come back to the original position. So, that is the idea. So, I have the code. So, I will give you some idea about the code, but before that, as we discussed, to begin with parallelization, first you should start with correct executing code, right? And second thing is you profile the code, figure out where my code is spending most of my time, and then you actually go and parallelize it only for those set of functions. So what we'll do is we'll first try to compile the code, right? Profile the code, and then we'll see how it works, right? So okay, so is the font size is okay, or should I increase the font size? Visible? Okay. Is it good now? Okay. So it's a makefile project because we got like bunch of different files, right? So I'll explain what exactly makefile is and all, right? So essentially, because I have like multiple files, I have written a makefile which essentially has like all the instruction to like compile the code, like what are the different flags we want to use and everything, right? So we have like, so I'll just briefly show you some of these different files. So essentially, if you see, this is matrix multiplication, then there is this DG for some global operations, then LGL. So sir talked about Lobato points and stuff like that, right? So build all that stuff. We have like different files. Just these are very small files, but just for simplicity, we have segregated into different parts, right? So you can just go ahead and figure out like what's happening, right? So we will be mainly focusing on the profiling output and only the time consuming parts of the code, right? So when I want to just compile, I have to just say make, right? So now it's compiling with certain flags. Okay, so we are specifically interested in this particular flag, right? Because I'm using GCC. GCC has this flag called as -PG. Essentially, these are two different flags clubbed together. So what happens with PG is, so we want to profile the code, right? And there is this nice GNU profiler which is called a gprof, right? When I compile this code with -PG option, it will add some extra information within my executable. And whenever I run that executable, it will generate a file called as gmon.out. Okay, so that gmon.out file contains all the profiling information. So whenever there is this like -PG flag, automatically it will generate that gmon.out file, right? So you have to just run the code, then only it will generate the profiling output, and after that we have to use just gprof to see the profiling output. So I'll just try to run this code. So there are these two options. One is polynomial order and number of elements in one direction, right? So I'm saying, let's say 6 is my polynomial order and 300 is, let's say, my NEL, right? Number of elements. So it's in one direction. So it's running, it will take some time. So while it's running, okay, it's collecting that profiling information because we have passed this -PG flag, right? So whenever any function is getting called, it will like log that start time, end time, and all those things. And that information will be again stored in that gmon.out file, right? So it's running for, I believe, some 500 or 1000 iterations, not like full code, right? Full code will take some lot of time. So we'll run it for only certain amount of time, and then we'll just profile the code and parallelize it, right? Yes, sir. This is DG is discontinuous and CG is continuous. DG is discontinuous Galerkin and CG is continuous Galerkin. So this is DG. Yes, DG. Discontinuous Galerkin. Yeah, so any other question? Okay, so, okay, so this is taking like slightly more time. Okay, okay, I don't know. let me kill. Maybe just a second. Yeah, so I'll just show you the file then. So let me compile and run it from the different directory. Probably I might have changed something. Advection 6300. Okay, so while it's running, so let me show you that make file. So you can pass like which compiler you want to use and different flags, right? So I passed -pg here. Then while loading what flags you want to use, those flags, and these are list of files that we want to compile, and then it will be combined into a executable called as advection 1D. Okay, so this is like very simple make file. Probably if you are interested, you can know more about it, right? Okay, so it's running. So it's printing some time steps, and before that it's running something else. So I will go through the code also. So roughly for these many number of iterations, whatever n number of iterations we are running, it's taking 37 seconds, right? So now I'm interested in that gmon.out file and the profiling information available with that file. So let me open a new tab. So the command is gprof space the executable file name. Oops. Sorry. So it's printing some lot of information. Okay, I'll explain it in detail, right? So if you start from like the top, okay, so we get something called as like the main profiling output, right? So here if you see there are these different function names which we have used inside our code, and there are these like different numbers. So I'll explain column by column. Okay, this is one tool. Similarly, there are like different tools from let's say Intel, Nvidia, okay, and AMD, right? So this is a free GPU GNU tool, but you can go to nice GUI based tools also, right? So starting from the first column, if you see, it says like there is this percentage sign, right? So what it essentially says is that this first guy, first row, this function took almost 49% of the time, total execution time, right? Which is some 18.65 seconds, which is roughly like half of my 37-second execution time, right? So what it means is, okay, so this guy mat is essentially matrix multiplication operation is taking 50% of our execution time, right? And now we remember the Amdahl's law, right? So Amdahl's law says like if you want to achieve the highest performance, you have to parallelize the like most time consuming guys, right? So if I parallelize this guy, okay, roughly 50% of the overall execution time. So how much time, how much speed up we can achieve, like any upper limit or any theoretical number that you can guess? If I parallelize this guy and we use like let's say 10, 100, like 1000 or maybe million number of cores, what is the maximum amount of speed up I can achieve? Amdahl's law? Or forget about Amdahl's law, just common sense. If I have a code which takes 50% of the time, if I parallelize it using 2 threads, 4 threads, 10 threads, 100, 1000, million, right? So that execution time will like tend towards 0, right? So what is the upper limit on my overall speed up? Yeah, somebody said it correctly, right? 2, right? Because if I use theoretically like infinite number of cores, then this 50% will become 0, right? But still the rest of this 50% is running in serial. So remaining like 18, 19 seconds, it will anyway run, right? So maximum speed up you can achieve is 2. right? So just parallelizing the first guy is not really useful in this case. Then probably I'll have to look out for the next guy also. So next guy is again like some 21%. So roughly I can say that first two guys, if I parallelize, I'm parallelizing 70% of my runtime, right? Not code, 70% of my execution time, right? But still that's not enough, right? If I want to work on, let's say, like 100 or 200 number of cores, probably you have to keep going down, right? So that's the idea. So this profile essentially, it will sort this functions in descending order, right? So it will sort it based on the execution time in the percentage and sort in descending order. So the topmost will be at the top, right? And slowly, as you see here, like it will tend towards 0. So probably this line onwards, right? It's like not really important. So even if, let's say, there is this function, some random function, I know that this is really easy to parallelize, but it's not worth parallelizing simply because it's taking like almost 0% of the time. So even if you write a very efficient code for this function, you are not going to get any performance benefits, right? So our targets are the top guys, right? So it again depends application to application. So this application I would say really nice simply because there is one guy who takes roughly 50% of the time. But large typical codes, you might have like lot of different functions which might be taking like 15-10% of the time, and there will be n number of such functions. And if you want to run it on large machine, then probably you have to worry about even this tiniest guy, right? So this is like some 3%. You'll have to really worry about that guy also, right? So okay, so we'll start from the top, right? So this is like matrix multiplication, and the next one is matrix vector multiplication. So we'll try to parallelize it, but we'll first look at like other columns. So this was the first column. The second column is the cumulative seconds. Okay, so it's 18, then 26, 31. It's just adding up the seconds. So not so interesting for now, right? Then this third column is self seconds. So self second is essentially the time spent inside that particular function, right? So my matrix multiplication is taking like 18 seconds, 18.65 seconds. Then my matrix vector multiplication is taking roughly 8 seconds, and so on, right? So here I'll know like, okay, so for this particular function, how much time I'm spending out of my total 37 seconds, right? Okay, so immediately related to this column is the next one, which is important simply because just this self second is not really the indicative number. So you have to see how many calls it's making for that particular function, right? So for matrix multiplication, there was only one call throughout the execution of the code, which itself took like 18 seconds. Whereas if you see the matrix vector multiplication, it was called for almost 2000 times, and total execution time inside that particular function is 8 seconds. So essentially for each call, it's not 8 seconds. It's 8 seconds divided by 2000, which is the next self seconds per call, right? So I'll explain why this number is important. But if you look at the first one, okay, this is 18 seconds, but if you look at the second one, it's hardly 8 milliseconds, no, 4 milliseconds, right, for each and every call. So I remember like one of the professors mentioning that so your execution time should be significant so that you can see the performance benefits. So for example, let's say we want to parallelize this matrix vector multiplication, which every time takes like 4 milliseconds to execute, right? And if I put a hash pragma or MP parallel or whatever, right, 4 milliseconds can go down to 2 milliseconds, 1 millisecond as we increase the number of threads. But there is a theoretical limit it can go down, right? Because there will be some overheads for creating the threads and joining the threads, right? So these kind of functions won't scale like 128 cores or 200 cores, 500 cores, no. So probably 4, 8 or maybe 16 cores it will scale because the execution time for each and every call is too small. Whereas if you talk about the first guy, matrix multiplication, probably you can still keep on like increasing the number of threads and still get some speed up. So that's why, so this self seconds per call is also key. Okay, if you have like large number of this small functions, and if you just put in like OpenMP loops everywhere, okay, it's at some point of time it's going to degrade your performance. Okay, so maybe with 2 cores it might take 2 milliseconds, with 4 cores it might take 1.5 milliseconds, but maybe 16 or 64 cores it might take 2 or 3 or maybe in case 5 6 seconds milliseconds, right? So actually it might increase your overall execution time. So that's why like it's not like okay, so I can see this function and it's important and it's taking 21% of the time, I just go and parallelize it. No. So you have to look at like total execution time plus number of calls, and hence you get the per call time. If it is too small, then probably it's not going to work. So you'll have to work around this time, right? So there are like different ways. If we get some time, we'll talk about it. But if it is like 1 millisecond and it's being called for let's say 1 million times, okay, certainly creating OpenMP threads every time you enter into this function and then destroying it will kill your performance, right? So in that case, probably that may not be suitable function for parallelism, right? Whereas on GPUs, probably like 4 milliseconds is still okay, because on GPU the overheads are not that big, okay? So we'll see that part also. That's why we have a small demo for OpenACC, right? But any question in these like 2 points. So let's first focus on these two because these are pretty straightforward. The next functions are essentially calculating the inverse of the matrix. So LU inverse, backward substitution, and other stuff. So let's not get into that part. Let's focus on this function. So any questions on the profiler? Yeah. In some cases, okay, for fewer number of threads we can still do it. Yes, 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 yes. Correct. That may not be true. So we'll see the code and then I'll talk about it. So we haven't seen the code yet. Okay, so we'll come back to that part. So in this case, I cannot run these calls in parallel. Yes, because they are called inside our iterative loop, right? So I cannot run those iterative loops in parallel. It has to be in serial fashion. So, so any other question? Okay. So let's quickly look at the loop. Okay, then probably because anyway he asked that question. So this is my like main DG implementation, right? So initially I'm like allocating some of these arrays and stuff like that. Okay, so I'm just rushing through it. Then it's generating all these legendary polynomials, and it's setting up all the weights, quadrature points, and everything. So let's not worry about that part, right? So main interesting things start from like the initial condition, and just before that we had some initial setup, right? But for our discussion, let's only like begin with this. So there are some initial conditions, then like we are setting up these global matrices which we have to solve, right? So essentially you could see these two functions in that profiling thing, right? So matrix inverse, which in turn call LU decomposition and other functions, right? And there is this matrix multiplication, which is our 50% of my execution time, right? So if you see, I have commented it out for the full iteration. So when you actually try and run this code, you can just go back to total iterations. Right now, just for simplicity, I am running it for 1000 iterations, right? And this is my main time loop, right? So iterative loop. So I am using RK2, right? So this is RK1. Essentially, I am like for solving this problem. Okay, so first step is f is equal to 2 into q that I am setting, right? So it doesn't really take a lot of time, but here matrix vector multiplication will take some considerable amount of time, which will parallelize. Again, the next thing is also simple loop, okay, which won't really take a lot of time, and we'll talk about that part. So probably some of the professor might have already talked about the time complexity of a problem, right? So we'll briefly touch upon that. So if you see, RK2 is again similar, right? So you have like one for loop which goes from 0 to n, again like matrix vector multiplication 0 to n, same is repeated for RK2. So what is the difference between this loop versus matrix vector multiplication versus matrix multiplication in terms of execution time or in terms of number of computations? Any guess? What is the difference between matrix multiplication and matrix vector multiplication in terms of number of arithmetic operations we perform? So matrix multiplication is like 3 loops, right? So we call it as a n cube order operation. So the worst case scenario, it will execute n cube number of operations, right? Whereas matrix vector is essentially matrix into one column, right? So it's n square, right? There are only 2 loops, right? So as you increase the value of n, okay, let's say for 10, right? So matrix multiplication will be 10 to the power 3, right? Whereas matrix vector multiplication is 10 to the power 2. So 100 versus 1000, right? And as you keep on increasing your value of n, so for example, instead of this 6 300, if I say 6 is my polynomial order and 3 instead of 300 I say 500 or 1000, okay, that matrix multiplication will take really large amount of time because it's n cube, right? Whereas matrix vector multiplication is just n square operations, right? So this is like slightly like a different code, or I would say exceptional code, where the function which is called only once. So this guy, it's called only once. It's not part of my iterative loop, right? It's called only once, but still as I increase my value of n, this execution time will exponentially increase because I'm going in order n cube. Whereas this guy is going order n square, right? So as you increase the problem size, probably like this time will decrease the percentage and this time will increase, right? So I'm coming back to the original point, right? So when I want to profile my code, I want to just first look at, okay, so what are these percentages? But now these percentages depend on your problem size. If you change your problem size in this particular case, let's try that and let's see. Okay, so let me change it to, let's reduce it, right? Let's say for 100. Okay, let's run this thing again. Okay, now the execution time has gone down, right? So it's just hardly like some less than a second, right? So let's increase it and then see. So as compared to this 300, 400 should take really like significant amount of time, right? So this is 37 seconds, right? So probably it might take 100 or more than 100 seconds. Right? So any questions on this part? So the key point here is like when you profile your code, don't profile it on a very small example input test case that you have. You need to profile your code based on the actual problem you want to solve. Let's say you are working on finite volume, element, whatever. You want to work on actually 1 million grid size, right? But for testing purposes, you got like some 10,000 wala test case. Okay, if you profile it for 10,000 wala test case and based on that you parallelize the code, the profiling output or the weightages given to different functions might be different for the 10,000 wala case versus 1 million grid point case. So ideally you should be profiling the one which you want to run. If you want to run like 1 million or 10 million, you profile it for that case and based on that you parallelize it but test it on a smaller case. Otherwise you will see completely different results because see these are like straightforward applications where I know that it's n cube versus n square, right? But in many of your cases it may not be straightforward like n cube or n square. It might be more complicated than that, right? And as you change the problem size, the execution times there will significantly change, right? So you might even end up like parallelizing some of the code which probably doesn't take significant amount of time, right? So that's why this part is important. So let's see so how much time it takes. Okay, so any questions while it's running? Also there are some ways like the, other techniques where like you want to figure out what kind of test cases you want to cover, and probably professor already mentioned about error calculation and stuff like that, right? So because these are like floating point computations, your serial output will not match with the parallel output bit by bit, right? So if your serial output is like some 10 point something something, then your parallel output will also differ by certain decimal places, right? So you should have that tolerance and those things in place before you actually start parallelizing your code, because you might write a parallel code, but it might not give you the correct answers, right? So that's why setting up the test cases, setting up the tolerances, error tolerances which we can accept, and the error tolerances which we don't want to select. So those things you have to set up before you actually start writing the code, right? Okay, so while it's running, we'll go to the code, let it run. Let's open the matrix multiplication example. Let, yeah. So let's start writing OpenMP code for matrix multiplication. So I'll write couple of keywords, and you guys are supposed to tell me the next keywords. Okay, so what should I write after parallel for? So you guys learned OpenMP, right? This is a simple matrix multiplication example, right? So what do I write next? This is correct, right? Hash pragma OMP parallel for, right? So what's next? You can refer to your notes or whatever, like, or old slides. Okay, so first, okay, what exactly we are supposed to write here? What's next? Okay, reduction. Okay, what else? Okay, so another, probably I think professor already mentioned, but another good practice is you should always use default none. I'll come back to this discussion, but let's finish the other part. Okay, so we'll discuss why default none. What else? Okay, let's figure out like what exactly we want to write there little later, but what are the different guesses? What we generally write after this thing? After hash OMP parallel for? We have to specify the guys which will run as a scalar, private and shared, right? So you remember this clause, right? There is this clause for private and then shared, right? So which of these guys will be shared and private? So in any guess for first private, which are the variables should be private here? What is private? Okay, let's go there. What is private? There is this clause, right? This is correct, right? There is a private clause, right? So what is private? Yes, only accessible for that particular thread. So when I say I want to declare some variable, let's say j, I want to declare j as a private. What it means is every thread will have its own copy of j, which is private to each thread, right? Other threads won't be able to access it, right? So here, because this loop will be executed by each and every thread, right? And we are going to divide this loop across multiple threads, right? These two loops will execute as it is for each and every thread, right? It's just that only the I range will be divided among different threads, right? So j and k are obviously private, correct? So each and every thread should have its own private copy of j and k. Agree? What else? Do we need any other variable as a private variable? Yes? No? Okay, we'll come back. Okay, so which variables I should declare as a shared? Sorry? That's H1, sorry, yeah. H1. Why do you think that H1 should be shared? It's correct, but why you think that H1 should be shared? right. So value of h1 should be available to each and every thread, right? So that's why we can declare it as a shared, or we can say it as a first private, but let's not get into that. Okay, so it's safe to say that h1 is shared. What else? See, this is OpenMP programming, right? So if you can understand this part, then only you can go and parallelize your own code, right? And this is a very simple example. Sorry, I should be shared. Okay, first comment, we don't have to really worry about it because it's the loop which we are going to divide. So OpenMP internally takes care of it. But if you share it, then like different threads might override to that iterator. So we don't have to touch. So OpenMP will take care of it. What else? C, why shared? Why not private? Yeah. Essentially, C is full array, right? And every thread will work on chunk of that array. Okay. If I create a private copy of that array, then everybody will have a full copy of C array, right? Which is not something that we want. So what we want for typically arrays, we want to make it shared simply because like every thread will write to different location of that particular array, right? So that's why typically generally the arrays will be shared, not necessary, but generally that's the case. Okay, so what next? Sorry, obviously. Okay, A and B. Next, done, or still we have some. Okay, let's ask compiler. So meanwhile, let's check if that job is run. Okay, see. So this function, like this execution 6, 400 took about 112 seconds, and let's see the profiling output. Now you see that matrix multiplication is taking roughly 63% of the time, and matrix vector is taking just 12% of the time, right? So it has changed because we have changed the size of the problem. So that's why the correct size of the problem is really important, right? Okay, so let's go back to the compilation part. So okay, so any other variable you want to add? Anything? Or are we done? See, whenever you write your code and if you miss out any variable by mistake, okay, it makes it as a shared by default. And if you make some variable shared, and if it has like some side effects, then you won't get the correct answer. So you have to be careful, right? So writing one line is good enough for parallelization of the code, but what do you write here is the key. So are we missing something? Okay, so W1, W2. What else? We don't have to worry about it. Compiler will take care of it. Okay, so that's where my default none comes in. So when I say default none, okay, so compiler will expect us to explicitly mention like each and every variable either as a private, shared, or any other type of variable. But each and every variable that we are using inside this parallel region should be explicitly declare something, right? So we have to list out this variable, each and every variable here. So let's see what is the compiler output that we typically get. Let me make clear, make. Oops. Oh, I didn't save. Okay. Okay, just a second. Oh, okay. So I'm in open. Oh, sorry. So, okay, I'm modifying the serial code and compiling the parallel code. Sorry. Yeah, I think I have the solution here, but yeah, so this is what we had prepared, right, without W1, W2, and let me compile it again. Oh. Okay, so okay, so I don't know. Okay, just a second. So I don't. Oh, okay. So I have removed the OpenMP flag. Sorry. So I missed this F OpenMP flag, and that's why compiler is just ignoring the OpenMP statements inside the code. Sorry. So same thing can happen with you also. So if you see here, there is no F OpenMP flag. So any OpenMP code without a F OpenMP flag will be compiled as a serial code. It will just ignore the hash pragma statements. That's why it's not giving me that error. Right now it's giving me error, right? After putting the F OpenMP flag, it's giving me error. It says W2 not specified in enclosing parallel, right? And that's mainly because default none. Okay, if you don't specify default none, see, this is a very simple code. Okay, probably we can figure out easily, like which variable we missed out. But if you have a really long for loop, easily we can miss out some of the variables. So that's why default none is a really good practice. So compiler will tell you, hey, you didn't mention anything about W2, W1. You either specify them as a private shared or something else, but you specify it explicitly, right? So let's specify it, and then this error should go away. Compiling, right? So any questions about this? Because next function, okay, let's see. We'll quickly go through, but yeah. So this is like the topmost function that we have parallelized, and let's see how we can run it fast. So any questions? Okay, so what we'll do is you have already used this flag, right? OMP num threads, right? So I'm saying that I want to run it with 2 threads. Okay, let's run and we'll see. We already know that this guy takes some 112 seconds, right? Where is this code? Yeah, so it takes 112 seconds, right, for 6 and 400, right? So we'll run the same problem and let's see how much time it takes. So how much time it should take? Any guess? Divided by 2. So is it correct? Like if it's taking 112, it should take, like with 2 threads, it should take 61 seconds, roughly. Yes? No? Sorry? Exactly. So we are not like fully parallelizing the code, right? We have just taken one function and parallelized it. That function takes 63% of the time, or 71 seconds out of total 112, right? So essentially remaining 40 seconds it's serial, right? So that 40 seconds will remain serial because we haven't parallelized it. So this 71 should go down to theoretically half of 71, right? So it's essentially 35, 36 seconds. So 40 plus 36 is essentially the number. So 75, 76 seconds, or somewhere near, like 75 to 80 is the number that we should expect. Okay, it's still running. Okay. Oh, wait. So probably I might have changed the total number of iterations. 1000. Okay, it was for full. Yeah, 77 seconds, right? Roughly in that range, correct? So let's see with 4 what happens. Any guess now? Sorry? So 40 plus 71 divided by 4, right? Roughly. So let's say like 18 or 20 in that range, right? So somewhere around 60, maybe. Let's see. And then we'll directly jump to 8, 16. So this system got like 64 core processor. So we can theoretically go till 64. So let's see. So any questions while it's running? Okay, no questions. Okay. Right? In that. Okay, so let me jump directly to 16. So we don't have enough time. So let's see for 16. Any guess? Somewhere in the range of 40 to 46. Sorry, so 45, 46 in that range, right? Let's see. So I know that I got like 64 cores. So what do you think I should be using like for number of threads if I want to run it for real life application? If this is a, let's say, this is a real life application. Okay, this is 45, right? So should I be using 4 to 16 or 64 or 128 or any number? So what do you think? Where I should get the best performance? Any guess? 64. Okay, so let's try 64. So 64 should take how much time? Roughly 41, 42 in that range, right? Let's see. How about 128? What will happen if I got like only 64 number of cores? I think there was some discussion about it, right? Yes, so we are coming to that point. So if I look at like these execution times, okay, so for 4 it's 60, for 16 it's 45, but if I go to 64 and if goes to let's say 42 or whatever, right? So from 46 to now we got like 42, right? So now we are using almost 4 times more resources and I'm able to just cut down 10% of my overall execution time roughly, right? So it's not worth it, right? But let's try to saturate it with more number of threads. Let's say 128. Any guess what will happen? I got 64 cores and I think you could see the scaling, right? We're able to kind of linearly scale because this is a perfectly scalable code. Guess 41. 41, 42. Anybody else? Like less than 40? Okay, so more than 45 or 50? Marginally increased, right? Why is so? Okay, so let me try 256 and then we can. Yeah, so why it increased? Any guess? We are not communicating, right? This is not MPI. This is OpenMP, right? MPI we are doing some send receives and all those things, right? Here it's like independently. So I have this array I. So I'm just dividing this range. I'm just dividing this full range, right? Whatever like 1 to n into those mean number of threads, right? So why is it increasing and what will happen with 256? It will increase or it will decrease? Roughly the same, right? So again it depends, but the key point here is it slightly increased from the ideal 64 cores, mainly because as sir was yesterday discussing, right? So you have multiple execution units, right? And we are already saturating them inside each core, right? So even if we oversaturate it using either hardware level multi-threading or software level multi-threading, hardware level multi-threading is something that sir discussed yesterday, right? That hyper-threading concept. So internally processor will take 2 threads and try to map it there. Whereas software level multi-threading is this, right? So I created 128 or 256 number of threads, even though I know that I got only 64 cores, right? So what will happen is OS will try to schedule 4 threads to single core in round robin fashion, right? One after the another. It will give you some small chunk for one thread. It will take out that thread. It will assign next thread because now we have more number of threads than the actual cores, right? So somehow OS has to make sure that every thread is able to run. So this switching between the threads is essentially causing the extra overheads, right? And that's why we are spending more time, right? If I create more number of threads, it's just like adding the overhead of switching between the threads. So that's one overhead, and another overhead that we are not going to discuss today, but briefly I'll mention is like when one thread is running on one core, when it jumps from this core to another core, right? The associated data for that particular thread in the array ABC might be near to that cache, right, for the previous core, right? So you will end up having those issues, right? So this thread was running here on this core and there was some cache here. So some temporary data is available here, but next time OS decided to take this thread from this core to some other core, then again it has to fetch that data, right? So there is penalty in terms of moving around the threads from one core to another core. So typically what we also do is we say that we want to lock the threads to the given core, right? So we say that okay, this thread once it assigns to this core, it should always run this core. It should not go other sides. Same way, there is another way say that two neighboring threads probably accessing the neighboring values, right? So there are different ways by which we can divide these threads to different cores. So let's say I have these 64 threads, right? So those 64 threads can go to any random cores because I got like 64 threads, 64 cores. They can go to random cores, right? But if they go in sequential fashion, then neighboring cores can probably share the data and you will have some cache benefits, right? So that is also, so those things also will affect your performance. We are not really worrying about that part now, but if you want to fine tune this number further, okay, so you have to think about all these things, like how the threads are getting locked to different threads or jumping around and things like that, right? And this particular chip is a chiplet architecture, so essentially it's not a full single die of 64 cores. There are 8 different dies of 8 core each, right? So these are smaller different chiplets connected together on a single chip, right? So there are again penalties related to that. So let's not worry about that, but final level of optimization will be focusing on those numbers. Yeah. So anyways, let's quickly come to the matrix vector multiplication. I think it's like fairly straightforward, right? So here I'm using this TMP sum, right, for summing it up, and then finally I'm writing it, right? So that's why it has to be private. J I'm using it here, that's why J is private, right? And there are these ABC are shared, and N is my total number of number of rows or column, that's N, right? So that's why this is a straightforward code. So let's not worry about this part. So let's compile. So how much performance benefits should we expect when I run this code? Okay, let me open this part again. This is my situation. When I parallelize both matrix multiplication and matrix vector multiplication, what kind of performance numbers I should expect? Let's say 2 cores. So let's start off with 2 cores. Set 2 threads, compile it again, compiling successfully, running it. So if I parallelize both matrix vector multiplication, matrix multiplication, these two both, using 2 threads, what should be my ideal execution time? Sorry, 72. So essentially, see, it's easy, right? So I know the cumulative seconds, right? It's 85. So both these guys are parallelized. So essentially, 85 should go to half, right? And remaining whatever, like 15 plus 27 seconds. So 27 seconds is my serial part, which I want parallelize, which is like the next guys, correct? And this 85 should become 42, 43. So 43 plus 27 should be roughly 70, right? Let's see. Correct? Let's see what happens. Fine? Yeah, so let's directly jump to, let's say, 16. So let's not spend too much time. So for 16, any guess? Again same, 85 divided by 16 plus 27. 27 is my serial component, right? Parallel component is 85 divided by 16, right? So essentially 5 point something, so essentially 6 seconds roughly we can assume, and 27, so 33 seconds. Okay, let's see. Correct? Okay, let's jump to 64 and then we'll move on to GPU. So for 64, any guess? Again, like even though I'm increasing my number of threads, okay, the performance gain is like okay, so from 2 to 16 it was significant, but if you see the serial component of the code, it's still 27 seconds, right? That's still significant. So if I add these two percentages, it's essentially like how much? 75% of the execution time, right? So even if I run like million number of cores, I'm not going to get more than 3 times speed up for my full application as compared to serial. Roughly, right? Because this is 75% and then 25% is still running. 4 times speed up is the best that we can achieve, right? So we cannot go beyond that. Let's see how much time it takes. So that's why the Amdahl's law is important, right? So even though we parallelize like top two, which are taking 75% of the time, you'll have to sit down and parallelize next, like these three guys at least, okay, which will be somewhere around, I would say, plus 10, 10, 13, again some 24% of the total time. So roughly 99% of your execution will be in parallel, then only you would be able to achieve at least 100x or in that order, not beyond, or at max 100x, not beyond that, right? So, oops, it's taking more time. So while it's running, any questions? Because I'll directly jump into GPU, I'll just show you the execution time and then we'll come back to this part. Because I may not have time to discuss the GPU implementation as such, but I'll just show you the similarities between the OpenMP and OpenACC. Okay, it's really taking a lot of time. And by the way, we can really check if it is actually taking those min number of, okay, done. It's over. Oh, it seems to be hanged. Oh. Okay. It's not running. Okay, so I think it's hanged. Okay. So let me run it again. So it's hanged, I guess. Sorry for that. Let me 400. So for some reason this is hanged. Anyways. So I'm running it again. Let's see. So it should be 27 plus something, right? 33. Not 33. Yeah, 28, 29, right? In that range. Let's see. Yeah, 28.5, right? So at least we can say that it's scaling linearly because it was a pretty simple application like matrix multiplication, matrix multiplication, right? So certainly, so the code, I will share the code with you, so you can certainly try parallelizing this part, right? So only point I want to mention is probably, okay, so these two guys are still significant, right? And if you can figure out like how to parallelize them, okay, so you'll get like reasonably good speed up. But okay, coming to this guy, if you see the self call for like time spent in each and every call is less than 10 milliseconds, right? And if I just divide it, it's roughly about 2 or 3 milliseconds, right? 2 in fact, right? So then like this may or may not scale to, let's say 64 kind of number of cores. Probably some additional performance penalties might incur, but I think until unless you play around and try it out, you won't learn much. Okay, so I'll leave these three guys with you, and probably you should be able to see like really good speed ups, at least up to 32 and maybe if possible for 64, right? So let's quickly jump into GPU part, because anyway we are going to talk about the GPU in the next session, but I just wanted to give you some idea about the GPU, right? Not the like hardware part, but the programming part, because there is this method called as programming language called as OpenACC, where you can easily parallelize the code, something similar to like OpenMP that we have, right? So let's look at the same code, right? And now we are using this new pragma. Okay, instead of OpenMP we are using OpenACC, right? So this is the syntax hash pragma ACC parallel loop, right? So now you might have seen like I have mentioned this collapse 3, we'll discuss it in a minute. But I haven't mentioned private or shared anything here, right? So that's the key advantage here. So okay, I wouldn't say like this compiler is smarter than the OpenMP compiler, but the point here is OpenSCC assumes certain things, right? So in many cases, all these like non-array variables, which we call it as a scalar variables, are generally treated as private or first private. What it means is, by default it will assume that W1, W2 are private or first private. First private when you have some value assigned to it, right? So here by default W1, W2 will be assumed as a first private so that their values will be available, okay? So you don't have to really worry about it. And typically all the arrays, which we typically call as vectors, will also be assumed as a shared, right? So whatever we wrote here previously, right, private shared, you don't have to explicitly write it, right? It will assume certain things. Okay, so if you have a exception to that rule for a given code, here let's say you want this W to be explicitly shared or something like that, you can mention it here, but in many cases you don't have to really, right? So here just writing this like couple of keywords, I'm able to parallelize the code. This is the actual working code. I'll show you the output also. And for the next loop, again same, right? So I just mentioned Hashpragma SCC parallel loop collapse 2. So we will talk about collapse, but yeah, this is a very simple. Just write this and your code is actually running on the GPU. Okay. So those who know CUDA probably like they might say like, "Arey kya bol raha hai?" Like but with OpenSCC we have some additional flags which will allow us to really ignore all our data transfers, right? Which is good as well as bad thing, okay, depending upon your application. But maybe in the afternoon Bharat will talk about it. Okay, so let me open my OpenSCC make file and I'll briefly mention some of these flags. So I am specifically mentioning this flag called as managed. Okay, so what it essentially says is that you don't have to transfer the data from CPU memory to GPU memory. So in GPU programming, you have two memories. One is CPU memory and another one is GPU memory. And if you want to work on the GPU, the data should be available in the GPU memory. Then only you can work on it, right? So with this managed flag, the hardware itself will make sure that whenever you need to access any variable, if the data is not available on the GPU, it will fetch it from the CPU and it will provide it to your program. So this managed will take care of all that business, like transferring the data from the CPU to GPU and all that stuff, right? And there are these other flags, let's not worry about it. Okay, I'll show you the output and that time I'll tell you. And there is this ACC minfo, it will tell you whenever we are actually generating OpenSCC code, it will give you some information about where it has parallelized the loops and all those things. That I'll also show you, right? So with these flags, you can essentially just put two lines, these couple of flags, and your code is running on the GPU, right? And let's see, just a second, let me check the number of iterations that I'm running. Okay, it's 1000 and yeah, here it's also 1000, right? So let's try to I'll say make clean Mac. So it's compiling something, right? So I'll briefly mention about all this information, right? So here this CC70 is the actual architecture of the GPU where I want to run. So I'm running it on a NVIDIA GPU V100. V100 is the model name. So for that we have to specify this flag. So now it knows that it has to generate the compiler has to generate a code for that particular specific GPU, and this PTX info output is this information. Okay, that may not be like relevant to us in this session, but next session probably a lot of these things will be clear. So it tells me like okay, so I have generated this particular parallel region, okay, and it uses these many number of registers and other stuff. So advanced information it's providing me, and there is this flag called as this minfo ACC. it's giving me the information about how it's generating the parallel code. So if you look at this highlighted information, okay, if you see matrix multiplication, it says at line number 39, right, I am generating NVIDIA GPU code, okay, and 39 it's creating these many vectors, it's collapsing and all those things. Probably in next session it will be much more clearer, right. So it's saying implicitly copying in AB, so automatically it will try to transfer the array AB and it will copy in as well as out for C. So those things will be clear in the next session, but it will give you all this information and it's automatically done by the compiler. We as a programmer, we don't have to worry about it. Okay, it's a nice marketing term, but in many cases that's true, but in some cases because we ignore this part, we may not get the correct answer or we might suffer performance losses, right. So you have to be careful about, and that's why we typically tend to read this information every time, simply because I don't want to miss out some information, right. So okay sir, so sir, it's deleting those files. So actually I have commented out, this is for these lines. So what I have is actually we can run it to actually generate images as well as movie. That part I have commented out. So it's saying that I cannot delete these files because those files are not there. It's not compilation error. This is like make file trying to delete this. There is this image directory and I dump the output as a text file and convert it to the image. So that image and the movie, those files it's not able to clear. That's why it's an error. It's not actually error. So compilation starts from here. So we are using NVIDIA compiler, that's PGA compiler, PGCC for compiling this code. Okay, we see it's compiled clearly. So let's say advection 1D6 400. Any guess how much time it should take? Just wildly guess. Same code, we have parallelized same set of functions, right? The only difference is CPU versus GPU. Minimum, maximum, 47, 40. Okay, so why is that? Like, okay. So what is our serial time? 27, right? Serial component in my parallel code, parallel version, after roughly some 27 seconds, right? So anyway, whether I use GPU, CPU, cluster, supercomputer, it doesn't matter. Okay, it cannot go below 27 because I haven't parallelized it. It's still serial, right? So minimum 27. Maximum could be, we don't know, depending on the GPU, things will change, right? So let's see. So any questions? This is just a small demo so that I just wanted to give you idea between OpenMP and OpenSSE. So any questions? $35. So any guess why 35? Okay, so when I run on a GPU, so there are two types of cost involved. One is actual running of the code. So it will take some few seconds or milliseconds to execute the compute part. Plus I need to transfer the data from the CPU to GPU, right? And GPU to back. So probably in next session you will see those things in detail. But so when I say it should be minimum 27, right? Whatever extra 7-8 seconds that we took, it includes both computation of the both the functions as well as the data transfer costs, right? And this may not be an optimized version of the code, right? So I'll not get into the actual profiling of the code, but it might be doing lot more data transfer unnecessary. Okay, that's also possible. So that we can only figure it out using a profiler, and hopefully in the next session probably they will show you nice profiler where you can actually see the data going from CPU to GPU, GPU to CPU. If not, maybe in the evening I can just give you a small demo. Okay. So any questions? Okay, right now we are using full GPU. So on GPU, essentially you cannot say that I want to use only 10 cores, 20 cores, 30 cores. Okay, if there is no other job running on the GPU and if enough number of threads are available, okay, so we like fully occupy the GPU. Okay, so I forgot to mention one quick thing. Yeah, this collapse thing. Okay, so I said like okay, so what? When I was using OpenMP, I was just trying to parallelize this loop. I just said that this is my loop and just divide it into chunks and give it to different threads, they will independently work, right? But GPU, the key requirement is that you need to have really large number of threads. Okay, if you ask me, I would say 1 lakh, 2 lakh, 1 million, okay, that's the number. If you create 100 number of threads on the GPU, you won't beat like CPU performance. GPU needs really large number of threads, right? Whatever number of threads you can create, if you can create 10 million number of threads, you better create it. Whereas CPU, if you create, forget about 10 million, even if you create like 10,000 or 1 lakh number of threads, probably it will crash, right? So CPU, the rule of thumb is essentially the number of threads should be less than or equal to number of cores. Whereas GPU, whatever maximum number of threads you can create, maybe in millions, that's great. Okay, so to increase the number of threads, what I am saying is, okay, so multiply this H1 into W2 into W1. Okay, that's why I am calling it as a collapse. So essentially, running these 3 independent nested loops, what I am saying is, compiler had just merge these 3 loops and create a single loop, okay, which goes from like 0 to H1 into W2 into W1, which is some, here in this case should be some in millions number, right? And that's how we get the performance. If I just remove this part, then your performance is really bad, and maybe you can try it out yourself. Without collapse, because it will just create threads which are exactly equal to H1, not more than that, and H1 is not that big, right? So that's why collapse flag I have used, and similarly here I am using collapse 2, right? So if there are no questions, then we'll break for lunch and we'll see you at 2 o'clock. Okay? Yes, sir. Sir. Yeah, question.
Okay. This was a question which was asked for the previous session.
Previous session.
So the question was from Mayur Patil.
No, Mayur Patil you have answered.
Oh yeah, citation. On the few slides where you mentioned DG methods are both power and computationally efficient, along with better scalability, why aren't we using it instead of FE methods? The answer to that is that FE methods have been established for nearly 60-70 years now. DG methods have just about being started in development in the last 10 to maybe 20 years. Slowly, so the adoption will be there. There's a wealth of knowledge in finite volume methods which has been established, and lots and lots of codes which have been written in that time. So you cannot abandon this wealth of information. So that's the reason why we continue to use it, and DG is sort of some nascent technology which we're still using. Yeah. Okay, the next question is, are there any cons for DG in solving small scale problems? Yes, the setup cost for DG is a little bit higher compared to finite volumes. So if you're doing it for extremely small problems, then probably DG is not the best way to go. So you have to have a sufficiently large problem for DG to be more efficient. For example, the higher order integration, higher order interpolation, is computationally intensive. By computationally intensive, I mean like, so you have to work hard on the local data. The fruits of that comes up only when you have a large enough problem. Yeah, that's only question. Any questions for Mandar? We are already just past 1. I'm sure you're all waiting for lunch.
For OpenACC or OpenMP?
Yeah, for open.
ACC.
Yeah.
I think like next section they'll cover some of it.
No, no. My question is
Ah.
the syntax for open parallel. After that, we have to end the code for open.
Okay, so you are saying like end hash pragma end parallel,
Yeah.
that part, right? So by default, like it's applicable for the immediate block, right? So even if I don't mention it here, like you want to say like this thing, right?
Yes, yes.
So on like in C you don't necessarily need it, right? So by default it's this block is like applicable.
So I'll answer it in a slightly easier way. For that for, you don't have to do an end for, right? It's automatically assumed where the for ends. It's very similar. So the pragma picks up that for, and the end of that logical block is the end.
Yeah, maybe in Fortran probably again like in Fortran also we have like end do and stuff like that. So there also if you can just don't mention it, still it's okay.
It depends on how the compiler parses the semantic. The compiler understands that the moment you put that, the next complete block is going to be offloaded onto the GPU.
So any other question?
Okay, so let us not hold you between this thing and lunch. I think the lunch is already served in the guest house. You guys can get over. People who wanted to stay an extra night, Good afternoon and welcome back to the last afternoon session, probably the most exciting session in terms of GPU computing. So today we have Bharat Kumar from NVIDIA with us. So Bharat and I kind of go back a long way. He's an ardent GPU enthusiast and has been in this field for a significantly amount of time. So I'll hand it over to Bharat to talk to us about GPUs, about OpenACC, and all the wonders that GPUs can do. Bharat, over to you. Thanks.
Thanks a lot, sir. I hope you all can hear me till the end. Is it audible? So I'm here to take a session on a different architecture, and you will hear this word from me quite a lot, which is architecture. Right? There are so many architectures out there when I talk about processors. The processors that you have primarily in your desktops or your laptops, Intel architecture you would already seen is x86, x64, right? That's what the architecture is called as. What's the most prominent architecture in your mobile phones? It's ARM, right? So it's an architecture. Now why do you need so many architectures? Because every architecture is different from the other architecture and they all have their own characteristics why they were built for, right? Similarly, GPU as an architecture stands, as in the name, stands for graphics processing unit. Now you might wonder why a graphics processor is being talked about here, because actually GPU as an architecture was fundamentally a parallel computing architecture. It was supposed to solve a problem which was created because of a workload which was called as graphics. If you see what is graphics, graphics is fundamentally painting a pixel on the screen, right? So in the earlier days, the graphics was actually done by CPU. If you know, there were no graphics processing unit earlier. But then people started playing games, or when you started looking at more high dimension or high definition graphics, at that particular point of time, if the graphics was done by the CPU, a lot of amount of the CPU was spent in doing graphics rather than doing other jobs. What are the other jobs that the CPU has to do? Running the operating system, right? Running the jobs that you are running, Microsoft Teams, this, that and everything. So it was identified that if a general purpose processor like CPU does some of this task, then it becomes a problem, and this thing got created which is called as graphics processing unit. What it did was, it did this operation of graphics, it was offloaded from the CPU to the GPU. Now why is it good, why is it bad, all of those things we'll look at in terms of how GPU is basically a parallel computing architecture, right? And that's what we'll look at here. So let me just talk to you in general with respect to the evolution itself. I know it's a couple of days that you've been looking at it, but my intention here is slightly different. So we started our journey where we used to have X number of flops, floating point operations per second, as we say, right? So we had single core with attached memory, which was basically the era of sequential computing. And all of our algorithms were designed like that. We were always being taught how to write sequential programs. It used to give around megaflops of performance, but then the applications demanded more performance and you had to move from a sequential era to a multi-core era. In the multi-core era, if you see, you had multiple CPU cores attached to the same memory, and hence it's called as a shared memory programming model, because all of them are sharing the same memory, right? But that's not what is also important. The important part is when the multi-core architecture came into picture, the software ecosystem to code it also had to change, which means now the programmer had to learn p-thread programming or OpenMP programming that you have learned to make use of all of those multi-core codes. If you wrote a sequential code, you were basically wasting the resources of the multi-core which were given to you, because a sequential core code will run on a single core, it will not run on a multi-core. So when the hardware changes, there is an era or a change in the software environment as well, is the part that I am trying to bring in. Then you went from megaflop to gigaflops, but you wanted more performance. Now it was almost impossible to get a lot of performance from a single node because of different limitations which existed. So the era of distributed computing came into the picture, where you could now connect multiple nodes to each other via a high speed or high bandwidth low latency networks like InfiniBand, right? So the idea was we move away from the shared memory programming model to distributed memory, because one node was not enough to give the performance that you wanted for your application, right? And that's where the distributed computing came into the picture, and the most prominent distributed computing programming model is MPI, message passing interface. Very prominent. It had its core into the high performance computing environment, but again, where did the responsibility fall? On the programmers. The programmers had to change from thinking shared memory to distributed memory, right? So again, there was a change in the thinking. When the hardware changes, the software has to change and keep on updating itself, otherwise you are not going to do justice to no matter what big supercomputer which is provided to the users. And that is one of the most critical thing which is there. Now with distributed computing, for a very long time, the way to increase the performance was you keep on adding more and more nodes. I had 10 nodes today, tomorrow I will connect 10 more nodes, 20 more nodes, 40 more nodes, but there is a fundamental problem with some of these things, right? One of the biggest challenge that you would see is scaling, which means you will obviously see the ratio. If you look at the ratio of compute to communication, which means the amount of compute you are going to do versus the amount of communication that you are going to do across, will have its impact on your application. Like if I had one node, if I take 2 seconds and if I run it on 2 nodes, if I split my work across 2 nodes, it should ideally reduce to 1 second, right? From 2 to 1. There should be a 2x speed up, but it will never be 1 second. It will have an impact because of the communication part of it, right? Because communication is, no matter what we say, is going to be slower than the compute. When you are there doing computation, computation is always faster than communication, and that is what it will be. To do this or to solve some of these challenges for a very long time, this is how you were getting a lot of performance improvement, but there is something which changed and which we call it as GPU. Again, as I said, GPU were traditionally used for graphics processing, but then there was a PhD person like some of you also who realized that GPU is actually a processor which can do lot of parallel computations. Why not to use it for non-graphics application? When I say non-graphics, I mean fast Fourier transforms, I mean convolution neural network inside AI and all. These are non-graphics applications, and there was a effort towards using GPUs towards non-graphics. I will talk about that later on, but the name given to that architecture for non-graphics was CUDA, or Compute Unified Device Architecture. The word architecture is very important, again I will say, because architecture is not about hardware alone. Hardware will remain, you will get certain flops. You need to build the whole ecosystem above it to make a particular processor really useful. If you cannot write program easily on a processor, then that processor is bound to fail. And that's why there were a lot of things which were developed there, including driver stacks, compiler stacks inside your operating system. Then there were newer algorithms which were also devised, because it was a different way of programming. So if you are talking about, say, sorting or things like this, typically you would have heard of merge sort, heap sort, but for in a parallel computing algorithm, there is another kinds of sorts also which are very popular, like bitonic sorts. Some of the sorting algorithm work at bitwise. Now what I am trying to say is that with the architecture change, there was an approach change or algorithmic changes also which were being done in the way you write programs. And yes, in the end the applications were using it, and one of the key reasons for that was that GPU basically had a particular advantage of giving you more performance, and we will cover that on why it gives more performance in the next couple of slides. But again, GPU computing is not about the hardware or not about those parts, but it is a stack of different software and different kinds of applications which are built over it, and I am going to cover a few of them later on, but there are more than 100 SDKs which are available, and the idea is that if you are writing matrix multiplication, you should never write your own matrix multiplication. It's good for learning purpose, but there are already someone who has written or taken the effort of writing the most efficient matrix multiplication in the hardware at instruction level for you. So we should not reinvent the wheel, right? If I am doing any kind of a fast Fourier transform, there are already libraries which are present there. So the best parallel code is the one which is written by someone who has spent their PhD on it maybe, right? And their whole effort went into just writing a parallel implementation of that, and we should be just reusing those libraries as much as possible. But let me take you back. Some of you would be from say computer science background, so you would understand this part, but let me take you back into the most first thing that we are taught in the computer architecture, which is the processors generally follow this architecture called as von Neumann architecture. Some of you would have heard it, but fundamentally for any processor that you buy, there are three key ingredients where the processor would dedicate their transistors to. Okay. The first one is arithmetic and logic unit. What does it do? It's your core. It does addition, multiplication, or whatever is the actual instruction that you want to execute is in the ALU. What is the second important part in this overall processor is the control unit. What does control unit do? It decides various things like what is going to be my next instruction. If you have written if and else statement, it needs to predict whether you are going to go from if or else statement. So it has to prefetch some of those things well in advance, because your code behaves in this fashion. In order to always keep it running, it needs to do some control logic, because you don't write practically one after the other instructions. You will have different branches in your code, right? Last is the cache. Cache is also very important. Generally, whenever we allocate memory, it goes to which memory part? It's called as RAM. It's your RAM, right? So whenever you allocate memory, whenever you do malloc, new, or any kind of allocation, it goes to RAM. RAM is good, but the problem with RAM is it takes a longer time to fetch the data from RAM to your core. Whenever core wants to execute anything, it needs to get the data from somewhere, right? Where does the data come from? The data ideally would reside in your RAM. RAM basically has a problem that it is sitting very far from the core. In order to fetch any data from the RAM takes a very long time, while the core is very fast. I said communication is always slower as compared to computation. You can do computations very fast, but if you want to take the data and load it, it takes very long time in the RAM. To solve that problem, it's like this, right? If I am trying to say eat a pizza, I am just giving a very rough example, right? If I am trying to eat a pizza, I have an option. If I had to go to the canteen where we just came from, the pizza can be made there and then it's going to come here. Instead of that, what is cache is very simple. Cache says that instead of going there, I am going to have a very small station here in this particular room or just next doors, where whatever I require in advance, I know that there is a dinner or something which is going to happen, I am going to prepare it and put it here with the ingredients, and I will make it here. So I will get the ingredients, I will cook it here, and then I will use it. So the idea is very simple, that I want to keep the data as near as possible to me. So the cache hierarchy kind of behaves in this fashion, that you want your data not to be stayed somewhere lower in the memory hierarchy. You keep on bringing it near and near to the core, right? So cache is faster than RAM. It is always faster. It is high bandwidth and low latency as compared to your RAM. So a large portion of your processor is also kept for cache, because if you don't have cache, then you will always keep on doing that back and forth communication, and computation time will be very low and the fetching will take more time. That's the whole idea behind these three elements in any processor. If I talk about CPU, where we have been writing those multi-core codes, the CPU is more of a general purpose processor, right? What do I mean by general purpose? I already told you, it is supposed to run different kinds of application. Right now it is running Microsoft PowerPoint, it is also running Slack, it is also running other things, it is running the operating system. It is supposed to run different kinds of application, right? It is more general purpose in nature. It can do all of those things, and that's why it has to decide to put those transistors in certain places. The first thing you would realize is that it puts a lot of amount of its space to cache. And I told you that you are going to run different kinds of application right now on this particular multi-core that I have on my laptop. So you need to have a lot of control logic, because you have to decide, should I be running this instruction, should I be running the next instruction of PowerPoint or something else. It needs to have a lot of I would say the logic in terms of doing the control part. And because you have the same real estate, you cannot go outside that real estate of the processor, a very less amount is going to the cores. What are the maximum number of cores you get on a CPU? Any guesses? Sorry? 128. You can also get cores up to 128 odd also nowadays, right? So the CPU, because of the nature, because it is more general purpose, it tries to have the control logic, the cache to a large extent, and it has lesser amount spent for the cores. On the other hand, the GPU is fundamentally meant for only one purpose. It is not as general as the CPU, it is meant for doing parallel computing, which means it is supposed to take a lot of amount of things that you want to do in parallel and just execute it, right? So it tries to put a lot of importance to the number of cores or ALUs. In the GPUs, you get few thousands of cores. There are different types of cores as compared to CPU, but you get few thousands of cores, not hundreds, few thousands, 10,000s of cores is what you get in the GPU architecture as compared to the CPU architecture, which means the number of threads that you can launch on the GPU is much higher as compared to your CPU. So the amount of parallelism that you can execute on the GPU is also much higher. As I said, that the amount of control logic it needs to have is not needed so much, because I am trying to execute the same instruction. GPUs fall in this regime that you might have also seen throughout this lecture, called as single instruction multiple data or single instruction multiple thread, which means every thread is going to execute the same instruction. For an example, if you are adding two vectors, what does it mean? You are taking from, for I equal to 0, I is less than 10, I plus plus, A of I equal to B of I plus C of I. What are you doing? You are taking different data but doing the same instruction. What is that instruction? Addition, plus. So this kind of a parallelism is generally referred to as single instruction multiple data or single instruction multiple thread. And GPUs are very good at that, doing that. And there you don't need to have so much of control logic, because you are not jumping here and there, right? If this, then do this, if that, then do that, this, that, and everything. So you are not expected to be moving around so much, so less importance is given to the control. And then yes, the cache of GPU is slightly different also, and we will talk about that in a bit. But what I am trying to tell you here is not the fact that GPU is better than CPU. That's not the point here. What I am trying to tell you here is every processor has a particular intention. Why ARM is more popular in the mobile environment? What do we need in the mobile environment? Sorry? Lightweight? No. Lightweight is something, yeah, but from a processor point of view. No? Power. Would you ever buy a mobile if your power gets low in 15 minutes or 10 minutes? Would you buy that particular mobile ever? The main intention why ARM is very popular, because from the bottom up it was actually made for power efficiency. It was always meant for power efficiency, which means if you are running any applications on ARM, it is supposed to consume lesser and lesser power so that your battery life is higher. That is why ARM is very popular, right? Similarly, GPU was always meant to be a parallel computing architecture, and that's why it was made for that purpose. CPU, when it started its journey, it was made for general purpose. It was supposed to run operating system. Operating system is supposed to be running all general types of cores, right? So every architecture has its own advantage and disadvantage, and mostly in your application you might have to combine different architectures also together because your application needs both sometimes, and that's what we will talk about, which is also referred to as accelerated computing or heterogeneous computing. So accelerated computing because you are accelerating something. Heterogeneous computing because you have two different kinds of processor working together. So you don't have just one processor which is the CPU, you also add GPU to it and basically make certain part of your code go much faster. GPUs cannot run an operating system. So whenever you write your code, and if you write a main function, it will always start from the CPU. And in between, wherever you want it to offload to the GPU, it goes to the GPU. Like your graphics, only the graphics parts get offloaded to the GPU by the applications, not the whole other execution. It still runs on the CPU, right? So this is kind of a cartoonish figure to say whatever I just spoke about. What you can see here is that a large portion of the GPU is more towards these blocks which are primarily cores, while on the CPU you have lesser number of cores, but they are more sophisticated or more logic is built inside it to run different kinds of application, more control logic and everything, and large portion of it is also dedicated towards the cache part of it. So this is what, so every architecture processor will be finally bound by the same laws of semiconductor industry, right? But it's just that the choice of where do you want to put more effort is the one which differentiates this architecture. So coming to the strengths and weaknesses from a point of view of CPU and GPU, as I said, CPU, the biggest strength of CPU is that it has very large memory. What's the maximum amount of memory that we can get in a system? Theoretically, you can basically have 2 raised to 64. Why 2 raised to 64? Because we have a 64-bit operating system, right? Nowadays we use 64-bit operating system, so your instructions can go from 0 till 2 raised to 64. So you can have so much of RAM which is in terabytes. So you can actually have terabytes of data which can be stored in the CPU RAM. The second thing is every core of the CPU is very, very fast. The CPU cores run at certain frequency, right? How do you measure how the core is running very fast? Whenever you buy, you would see a processor definition to be associated with gigahertz, right? The higher the gigahertz, the faster the processor is. So the CPU cores run at a very high frequency of 4 to 5 gigahertz nowadays. So that's why every core is very fast. So if you can fit your parallelism inside CPU cores, it is a very good architecture of parallelism as well, as long as you can fit. So if you have 128 cores, maybe with hyperthreading 256, you can be, if you can run 256 of those things in parallel, it's a very good architecture because every core is very strong, it can run very, very fast. And the smaller number of threads, as I said, can run very, very quickly on that. There are certain weaknesses also associated with CPU. The first weakness is it has very low memory bandwidth. I am not sure if this was covered or not, but let's take an application, very simple application which I just talked to you about. A equal to B plus C. Very simple, for I equal to 0, I is less than 1 million, I plus plus. Do you think it is memory bound or compute bound? How many memory operations are we doing? A equal to B plus C, how many memory operations, reads and writes? Simple, right? 2 reads and 1 write. A is written equal to B is read and C is read. How many memory operations? 3. So you are reading 3 elements. How many compute are you doing? Computation? 1. which is addition. So no matter what I give to you in terms of number of cores, if your memory cannot give you that data at that rate, is there any use of the compute power which I give, no matter how fast the compute is? No, right? Because I can do things very fast, but if it takes a long time for me to reach from any one location to the other, no matter how fast I can do those things, it doesn't matter, right? Like I can reach from Bombay to Bangalore very fast in a plane, but if after getting out of the plane, if the luggage takes 1 hour or 2 hours to come out when I get it, it is of any use for me? Maybe not, right? So that's the part. So the memory bandwidth of the CPU, which is the current one, which is quite prominent, is DDR4. It's called a DDR4, and it gives you at a speed of around 200 gigabytes per second. That's the range in which generally you get the speed of reading from your CPU RAM, 200 gigabytes per second. Yeah, so the other part is also like, I'm sure it might have been covered, but based on the data structure you use, if you don't use a very good data structure and if you are not cache friendly, then your CPU is not going to give you the performance. And because it runs at a very higher gigahertz, generally it consumes more power. So in the latest world, when we are talking about exascale computing and all, we don't talk about performance. We talk about performance per watt. How much amount of power I am consuming to get that performance. That is the main criteria nowadays for selecting a particular processor, right? So CPU alone may not be that great because they run at a very higher frequency. What about GPU? From a GPU point of view, the biggest strength of GPU is that it provides you very high speed memory, high bandwidth memory. The bandwidth nowadays that GPU provide you is in few terabytes per second. In GPU, remember in CPU I was saying gigabytes per second. Here I am talking about terabytes per second. So you can actually read from the GPU memory very fast. That's one of the, it uses a different memory, 3D stacked memory called as HBM, which is the one which gives that much amount of speed up. It has more number of compute resources. The number of cores, as I told you, the number of parallel operations that you can run on a GPU is very large. I will never use GPU for adding 100 numbers. I will use it for doing something for millions of elements, right? Because it's like killing a fly with a cannon. You won't do that, you will use the right tool, right? So you would use the right tool for the right purpose. GPUs is meant for massive parallelism, and that's what you will use it for. If you do it, what I told in the CPU side is if you can fit within the CPU cores is good. Otherwise, it's of no use, right? So it's also referred to as high throughput. Another thing about GPUs is that they are very green in nature. They are proven to be very green in nature, which means the performance per watt of a GPU is very high. That's why there is a list which gets published called as Green 500 supercomputer list. In that you would see many of the architectures. The prominent ones there are GPU. Most of the top architectures that you will see who are more green in nature, which consumes lesser power, are from the GPU. Now you might ask why. One thing about GPU is that every core actually runs at a very low frequency. So on a CPU you are running at 4 to 5 gigahertz. On a GPU it is running at only 1 gigahertz. So every core is actually running 4 times slower as compared to a CPU core. So if you run a sequential program on the GPU, it will be 4 times slower on the GPU. So it is not supposed to be used in that fashion. So that's why you say that low per thread performance. So every thread is going to be slower, but you are going to have thousands of threads, 10,000s of threads which are running in parallel, right? And yes, because we are giving a very high bandwidth memory, the amount of memory that the GPU gives is also reduced. Like the A100 cards nowadays come with 80 GB memory on, which is the HBM memory. It's not going to give you terabytes of memory, it's going to give you lesser amount of memory because you have to compensate somewhere, right? If I give you high speed at the same time, I cannot give you such a large memory with the architecture. So that's one of the disadvantages of the GPU. So if I were to summarize in short, to you the fundamental difference between these two architectures. I could put it in very 1,000 feet level is like if I were to go from here to the airport and if I were to take only one of you with me, I would choose a bike. Bike is much faster, right? You will reach the destination much more faster. But what if I had to take all 50 of you together with me? In that case, I will choose a bus because bus is slower, but it can take all 50 of you together with me, right? So you, in the end, if I were choosing a bike to take all of you, I will do what? Back and forth, back and forth, back and forth, right? Because I can take only one person along with me, right? While in case of the GPUs, you have so many of cores or so many of seatings, so you can actually throw it a very, very large problem and it can do all of that in parallel. Now think about graphics, what I was talking to you about, right? What was graphics? You are painting pixels on the screen. What is painting pixels on the screen? For every pixel you are defining red, green or blue value. And you have 1024 by 1024 pixels. So what were you doing? You are actually doing parallel computing, defining all of those parallelism. Here is the same thing. It was a parallel computing architecture, but you used it for what? Fast Fourier transform, for radial distribution function, for convolution, for matrix multiplication. It's still a parallel computing job. So GPUs are very good at doing parallel computing tasks, and that's what it was meant for. Then the good part is almost no matter which domain I touch, everything requires high performance computing and parallelism at this time. Whether it is computational fluid dynamics, whether it is molecular dynamics, or whether it is artificial intelligence training, whether it is video analytics, whether it is machine learning, whether it is AI inferencing, genomics, no matter which domain I touch, all of these domains require parallel computing or high performance computing, and that is the key thing where GPUs is being used for all of these things. But still at the bottommost layer, it's the same architecture, which is compute unified device architecture, right? So if you have an application which takes a very long duration, and if you think it can be made parallel, in that case GPU is an architecture to offload that work from the CPU to the GPU. This offload concept is, by the way, not something new. You would see offload concept also in the networking side. Earlier the CPU used to run even the networking stack. Nowadays the networking is actually offloaded to the networking devices. It doesn't happen on the CPU anymore. The reason is the same, that you want to offload the task which the other processors can do very, very efficiently. From a point of view of maybe what I'm going to do is, maybe I'm going to stop and see if there are any questions. We can take, if you have any questions you can just ask. If so far whatever you have seen, so far whatever you have coded, you can basically see if anything that I said was slightly different from your understanding that you have been having so far. Is the fundamental, the concept very clear in terms of the GPU? $100 CPU. You have a CPU core with 100, GPU say with 1000, and you launch the same application across both. No. So that's a very good question. The question is, suppose I had a particular application where I had 10 cores, and if suppose my application was taking 10 seconds, just an example, I attach a GPU. Now that GPU basically will have say a 10x more number of cores, so I expect the GPU to give me 10x speed up, which will reduce my time to 1 second. The answer is definitely no, because it depends on the application itself. I told you that application characteristic is not directly defined to the compute. It will have a component of memory also attached to it, right? So how well you have written the code, how well it is using your memory, and all of this thing will come. So in short, if I were to also say in the other words, was like the CPU, even though there are 100 cores, but they are running 4 times faster as compared to the GPU core, so that 10x becomes 10 by 4x, and then so it is not going to be exact. That's why I am saying compute is just one part of your overall thing. It does give you a theoretical evidence, but your actual application performance will be completely dependent on your application characteristics. Yeah, it's all there on the green 500 list. Maybe I can share it with you later on, because it will change from one architecture to the other. I don't have it ready in my mind with respect to Ampere, but I can give it to you later. It's not on.
I have vague information on this. I do computing on a CPU. I do computing on a CPU. I open a terminal and I start coding. How will it be different on a GPU?
Will it run on the GPU?
How will coding, putting the code together be different on a GPU?
How will it be different? We are going to do a demo of it and show you the code. So that's my next slide actually. Next to next slide is exactly that. So I'm going to show, like you can code in different ways on the CPU, you can code in n different ways on the GPU. And it's up to the programmer to choose the path, and that's what my next slide is going to be. Yeah. Within a node, yes, but you can basically use MPI plus GPUs to go across nodes. So you can keep on increasing. Now, if you look at the Summit Supercomputer, you have 25,000, so many GPUs across different nodes. So you can, that's how exascale computing and all is being defined, where you have thousands and thousands of these GPUs connected. So you can have like 8 to 16 GPU per node, and then you connect those nodes again, and that's how you can keep on also increasing that part. So you will combine MPI plus CUDA. So it will be a hybrid coding, MPI plus CUDA. Any other question? So I'm going to cover this part later on, but there was a question on how do I program on GPUs. Now, what you are seeing here is n ways to GPU programming. I am calling it as n ways to GPU programming. Now, the first and the most prominent way to use GPUs is by using libraries. Now, we don't expect any AI user to write parallel code, any artificial intelligence user to ever write a parallel code, because NVIDIA has already written all the parallel codes, all the CUDA codes, and integrated it with PyTorch, TensorFlow and everything. So user does not need to know that there is behind the scene parallel code written by an engineer, but it is going to consume the GPU. If you are going to do fast Fourier transform, there is a library called as CUFFT. If you are going to do random number generator, there is a library called as QRAND, right? There are certain applications that we are working together where we already have a library for different kinds of solvers, right? Now BiCG solver or Jacobi and all of those different kinds, there is a library called as AMGX or Q solver, right? Unless you are writing your own custom application, we expect the user to use already defined libraries, because it is already well tested across different architectures that we have. Yes. When I say public domain, everything is free to use. Some of them are in form of binary, some of them are in form of source codes also. If the demand is higher, then the NVIDIA goes and implements it for the users, or we collaborate with the users to implement it along with them. User can do it. All of our architecture is open, right? So that's what you're going to write a Jacobi code when in the hands-on session on your own on GPUs. So to give you an example, like as I'm saying that NVIDIA created the architecture and then the researchers used it in the way which we didn't even imagine, right? Like the user, when we created graphics, there was a PhD student who used it for non-graphics purpose, right? Could make use of GPU. I'm talking about AI. We had given the CUDA architecture and somebody used it for writing convolution neural network, and that's why that Big Bang was back, right? So the architecture is open. If it is a new algorithm, the researchers is free to use all of our stack, which we are going to do in this session, but otherwise we recommend to use the libraries. If suppose it's a new algorithm, that's the stack that you need to see above. The left hand side of the stack is standard languages. One thing that every researcher wants or every user wants is that my code should not be maybe sticking to a particular architecture. Like if I write a code on GPU, it should also run on multi-core, an example, right? I should not write different set of codes. This is one of the requirements that many users or domain scientists have, because they are saying that I don't want to write code which is going to only be specific to one particular hardware vendor. Now, what has happened over time is this has gotten as a request to your standard languages like C and Fortran. Now, C and Fortran language, I am talking about the language specification, I am not talking about a vendor. They have come out with new specifications, like if you are using C++, the C++11 and C++17 standard, if any compiler like GCC or anyone implements, they have to support something called as parallelism, right, using standard template library. So it is part of the standard language itself. Some of us who have written Java program, like I used to be a Java programmer earlier, Java as a language, by default internally, inherently in the language, it has parallelism, concurrency as part of the language. While it was not there in C and Fortran, it started its journey with a sequential world, but that has all been integrated now into the language. C++11 and 17 supports parallelism as part of the language. So every compiler who says that they have to implement it, they have to add parallelism to it. So your code basically becomes hardware independent, which means today I can run it on multi-core, tomorrow I can just recompile it to run it on a GPU, because the compiler is the one which is going to do that job for you, right? Same thing goes with Fortran. Fortran 2018. If you use Fortran 2018, any of the compiler, it supports something called a do concurrent. It basically makes your loop parallel and runs it across. You don't have to write any code. It is part of the language. So the first approach, or the approach which is becoming really popular at this point of time, is usage of the standard language features, because which gives you a guarantee because it's part of the language. So you can use it for a very long duration, right? It's part of the specification. Everybody has to adhere to it. Now, the disadvantage of it is language needs to be generic. So you may write a general code, and you may lose out on certain performance. You may not get the best performance that you want to have. While you are writing a very higher level code, look at this code, so simple, right? Do concurrent. I am just telling I want to run this particular loop in parallel. Compiler writes all the parallel code for me behind the scene. But there are problems which can arise where you may not get the best performance. In that case, to take more control of parallelism, there is an incremental performance that you can get by using developer assisted programming. I am using the word developer assisted programming or directive based programming. You have already written codes using OpenMP. What is OpenMP? Is basically a developer assisted programming, which means you are telling to the compiler, I think this loop should run in parallel. Let me give you a hint by putting hash pragma, right? So you are assisting the compiler. It's not automated parallelism, right? So you are going one step ahead, taking more control of the things, giving directions to the compiler. So it may give you more performance because you can expose things like how many threads you want to launch, which thread accesses what data. So you are taking more control over it. You can do those things, that's why you can get more performance out of directive based programming. So this is again independent of hardware vendor. There are specification. One specification that we are going to look today is OpenACC, where we are going to do the hands-on in terms of directive based programming. OpenMP also supports GPU using something called as OpenMP offload. So the new specification of OpenMP also uses GPU using a concept called as OpenMP offload. It runs on the GPU. Last but not the least, use the lowermost detail provided by the vendor. Like from NVIDIA, we have CUDA C programming, CUDA Fortran programming, and you can explicitly write and take control of everything. Like how many threads I want to launch, which thread accesses what data, when does it get, how does it get allocated. Lot of things you can control. Does this data go in a shared memory? Does this data go in a texture memory? Does this data go in this kind of a cache? You are taking control of everything. What does it mean for the programmer? You are making and getting the best performance out of the code, but you are making it less portable, and you are investing time in understanding an architecture. So if I look at it from a point of view of n ways to answer the question which was also asked is, we have provided all the hooks to the user. Now it's up to the user to choose whether they want to choose this approach, this approach, this approach, or that approach. If I want to finish maybe my PhD faster, I might go with directive based programming because I am a domain scientist and I want to concentrate. The tagline of OpenACC specification is more science, less programming. The reason behind that is because we want the domain scientists to basically focus more on science and lesser on the programming part and do that. But if there are many researchers who want to get the best performance, they choose the last approach as well. So this is what is the n ways to the GPU programming part of it. I hope that answered your question as well. You can choose any, so you can code, and that's what I will show you. Like suppose this is an example which is one of the most level 1 blast function, basic linear algebra function. So you are multiplying a scalar alpha to a vector x and adding it to another vector y. Now one way of writing that code is using directive based programming. Like if you have a code, you can just append it with certain hints and it makes your code run on the GPU or on the multi-core. Or the second approach is, if I knew that there was a library for doing matrix operation, I could have just changed my code to use the particular library called as cuBLAS, which is CUDA based blast functions, and I could have just replaced that matrix operation with a call to a library. Or if I were to take more control of parallelism in that particular case, and if it was a C code, I could now decide how many threads. You can see here the number of threads I am launching is 4096 by 256. I am taking control of the mem copy to the CPU and GPU. I am taking control of the thread ID to do certain operations, so I can make it more explicit and get the best performance in C or the best performance in Fortran as well. Last but not the least, if you are a Python programmer, the same thing exists. If you are a Python programmer, you can use something called a Numba or CuPy, and the same code that you could write using C or Fortran, you can do the same thing in a Python environment. Like here I am saying @vectorize this particular function, and my target architecture is CUDA. So it will JIT compile this code to basically convert it into CUDA C code and execute in parallel on the GPU. Same thing for Python. Same thing for C++ also that I talked about is the standard language part, and you can also do it in MATLAB in case you are a MATLAB programmer. I think MATLAB also supports almost all the function it has. If you have a PCT, which is Parallel Computing Toolbox license of MATLAB, then the GPUs can also be used on MATLAB. So just to summarize on whatever I talked about for this much of duration, is that GPU as an architecture is fundamentally a parallel computing architecture. CPU as an architecture is meant to be more general purpose. Both of them joined together solves the problem that you have for your real application. Both of them have their own advantages and disadvantage. You can code it using different approaches, and we are going to see one of the approach when we are going to do the hands-on part using OpenACC in the next session. which is a hands-on session. Any questions on the topic that I just covered so far? Nowadays GPUs are very popular, in the sense like I have a GPU on the laptop, you can have a GPU in your desktops, you can have the GPU in the servers, in the cloud. So it is something which also added that the same code runs across all the GPUs. They can run the same code. The only difference is you will have lesser amount of cores because it is smaller in size. Your servers will have more number of cores, right? While the GPU cores here, this one might have 100 cores, the server will have 10,000 of cores because it needs to be within that power budget, right? So the time it will take will be more here as compared to running it on a server, but the same code will run as it is. There won't be any change in the code. Any question? Because we are almost at the time of the break. It is exactly 3. So we can take a, we'll take a 15 minutes. Yes. So there was a request, and I think there was a suggestion that we could also talk about this topic called as AI for science or AI for CFD. And because AI is touching almost every field that we talk about, so we'll take a 10 to 15 minutes short lecture also on this topic. Hello. Start. So welcome back everyone. So we are going to spend some time in theory, but I think we'll try to do more hands-on, because that's what will give you an idea in terms of what kind of a speed up numbers that you can expect when you start using GPUs. So we have a sample code for you, and we will try to code it in a very simpler way, which is directive based programming. And one way of doing it is using OpenACC. So OpenACC directive, as I said, it is developer assisted programming, right? So you are assisting the compiler to tell which part of the code should run in parallel. So it is directive based. It is quite popular. One thing about directive based program is you can target it to different kinds of hardwares. So in fact, the hands-on that you're going to do, you will write one piece of code, only a couple of lines, and the same code will run on both multi-core as well as on the GPU. That's the target that we have for the hands-on session. So one thing about OpenACC, as I said, is actually it is supposed to be simpler for the domain scientist, and you would see that it primarily consists of only three kind of directives. One of the directive talks about parallelism, which is ACC parallel. The second directive targets the data copy. I told you sometime back during the previous lecture that CPU memory is different, GPU memory is different. So you need to do transfers between the GPU memory and CPU memory, so you can control the data transfer, which is the data clause. The third one is the clause with respect to controlling optimization. How many threads you should launch and all of those things is being controlled by the third directive, which is ACC loop, and you can define level of parallelism inside ACC. The main thing about OpenACC it was designed was, first of all, it is incremental in nature, which means you still have your sequential code. You can still run your sequential code. It is not going anywhere. That's why it's a choice from various developers, because your sequential code continues. Just by enabling certain flags or certain hints, you can make it to run on multi-core, on GPU or other kinds of architecture. Only by annotating the code, right? Single source codes, that's what I said. Rebuild the same code for multiple architectures. So you can write code once and try to run it across different architectures. It is a very low learning curve. I just told you that OpenACC is meant to be easy to use, and to start with, at least it doesn't take a lot of time. Later on, yes, when you start optimizing it and you start getting into more details, or you start making it MPI plus OpenACC and all those combination, you may require some additional effort, but otherwise it is pretty easy to learn. So let's look at the syntax. First of all, OpenACC is primarily for two languages, which are compiler based, which means C and Fortran. It doesn't work for Python. Python is an interpreter based language. It doesn't compile anything, right? So it is used for the two most prominent languages which are more evident in the HPC field, which is C, C++ and Fortran. And the syntax is kind of given here. So what you are saying is giving a directive to the compiler. A pragma is basically a special instruction, or it's a special comment to the compiler that you are supposed to execute the next set of instructions in a different way. Don't consider it as a regular sequential code generation. Directive tells what type of that instruction is. ACC tells it that it is a ACC directive. You have learned other directive in the previous lab. What was that other directive? OpenMP. So what did you use for OpenMP? OMP, to tell that it is a OpenMP directive. Similarly for ACC, in order to tell to the compiler it is a ACC directive, you say hash pragma ACC to tell that it is a OpenACC directive and not a OpenMP or other kind of a directive. Again, as I said, you have the directives and then you can add clauses to it, which can be more additions. So the code that you're going to work on for certain duration is the code of Laplace heat transfer. I think this code is quite something which is relevant for this section because we are doing it for CFD, and it's a very simple application and you might have already seen it. So the idea is to simulate the heat distributing across the metal plate. The kind of we start heating it from a particular stage, and then we simulate the thing distribution across the plate, and for that we are going to use Jacobi as our iteration method. It's very simple without going into a lot of details of equation itself. What you do is you take the neighboring pixels, top, bottom, left and right, do an average of it, and you continuously do it in a loop till the time you have converged, right? So if I were going to talk about the code itself, the code looks pretty simple both in C and Fortran. So you have your while loop, which is till the maximum number of iterations have reached, or you have the threshold value. You go through the matrix, which is your metal plate which is there, and you take the neighboring values for every grid point there, and you do an average, basically divided by 4. You find the max of error, so you try to do this reduction operation, and if you have converged, in that case you come out of this loop. So that's what it does. There is also a swap operation. You would see that in order to make it parallel, you are first taking the input from A, calculating the new value and storing it in A new, but for the next loop again when you come, you want to have this new value transferred to A, because that's what becomes your input. So you are swapping the output with your input value, right? So you have couple of loops. The outer one is the convergence loop, this one is the loop for doing averaging, and this loop is for swapping the input and output arrays. So that's what it is, and I will be talking about profiler driven development in a bit when I show you the hands-on part also. But for everyone who is working on this kinds of code, this cycle is called as APOD cycle, or analyze, parallelize, optimize, debug. There is a debug component also there, but every programmer goes through this cycle, where the first thing you have to identify is, or theoretically understand, is which part of the code should be made parallel, because it's also referred to as Amdahl's law in case you want to project on how much speed up you can actually expect. To give an example, if your code was taking around 2 seconds, out of which there are say 2 functions, one of the function takes 50% time, another function takes 50% of the time. So out of 2 seconds, function 1 takes 1 second, function 2 takes 1 second, and I can only make one of the function parallel because the other function is doing maybe file IO, right? So what is the maximum theoretical speed up I can expect in this application if I make it parallel, before even making it parallel? So again I am repeating, my application takes 2 seconds, it has 2 functions, function 1 and function 2. Function 1 I can make parallel because it is parallel in nature. Function 2 I cannot make it parallel because it is sequential or it is doing file IO operations. If I make this code parallel, no matter which hardware architecture it is, what's the maximum speed up I can achieve in this application? Sorry? 2x only. You can reduce from 2 seconds to 1 second only, because the 1 second is always going to remain, right? So this kind of calculations or these types of projections, like how much part of the code is taking what amount of time, and if I make it parallel, how much speed up I can expect, is the necessity for any parallel developer. We can't expect that if I write a code only for application of a part which is taking 10% of time, give it 10,000 codes and expect 10,000x speed up. No way it can happen, because your application is bound by the other sequential part, right? And that's the cycle of analysis for which every programmer needs to understand and use tools. Don't do it on your own. Use tools. Tools are there called as profilers, which help you in understanding your application where it is taking time. These are called as hotspots. Once you understand it, you move to the next step of then parallelizing it. Never start directly without understanding those things. So I'm going to talk about that in a bit. I will show you a profiler demo as well. In fact, the code that you are going to write has syntaxes for profiling, and you will be able to profile it and see how much time is spent where. So the first part is parallelize, then we are going to look at, if time permits, we'll go to optimize, but our first target is to look at how can you make the code parallel, which is going to be the lab 1 for this particular session. So for OpenACC, as I told you, the first directive or the first pragma is OpenACC parallel loop directive. So when you add OpenACC parallel directive, like if you had a piece of code that you wanted to run in parallel, in that particular case, before or after, like here you are adding curly braces in Fortran, you will have the same equivalent thing where you have the start and the exit part of it. But if you make, or say hash pragma ACC parallel, this is a way of expressing parallelism to the compiler. What it does is, it actually creates multiple gangs. I don't know how did they come out with that word, but it creates multiple gangs. Okay? Gangs of railway workers. Okay. So it creates multiple gangs. These gangs work in parallel, right? They work in parallel to execute this part of the code. But there is a problem with this approach, is that when you add parallelism, and suppose you had a for loop here, what you are saying indirectly is, I am going to create multiple gangs, and every gang is going to execute this for loop. Is good or bad? It's bad, because everybody is doing the same work, going from 0 to n, 0 to n, 0 to n. Everybody, even though running in parallel, is doing the same work. You have not splitted the work, right? So in order to split that work across the gangs, you have to use another pragma called as loop. So what you are telling to the parallelism is, you split the loop into multiple gangs and run it in parallel. So you split the work using the loop directive. So you define parallelism and then you define what needs to be split using the loop directive. In fact, many of the times, so this is the Fortran syntax, by the way. So you have the parallelization of a single loop here, hash pragma ACC loop. Same thing is in Fortran. In case you are a Fortran programmer, if you are going to use Fortran, instead of hash pragma, you have exclamation dollar as the specialized comment with ACC and then parallel, right? Just make sure it is at the right, based on the Fortran version you use, you have to make sure, because it is a comment, right? So comment is a special comment, compiler is free to ignore it, okay? Compiler can actually ignore the comment. It feels it's not the right comment, it can ignore it. So you might feel you are running in parallel, but actually you might not be running in parallel. Especially in Fortran, this happens where if you don't put the right set of spaces and all, the way you have to do alignment, then this comment gets ignored and your code actually is running in sequential. And we'll see how to look at that part also, how to make sure that if the compiler has actually created parallel or not, right? So this is how you define parallelism, and this parallelism is so common that generally you can write it in one line. You don't have to write two lines. You can just say hash pragma ACC parallel loop or exclamation dollar ACC parallel loop. You don't have to write it as two different instructions. You can have it in one instruction itself. So the code that you are going to work on, what you are going to do is that you will be taking this code which is sequential in nature, and you are going to add these pragmas to the code, to the loops. Okay. One thing that I am saying is, you add the pragma to what? To loops. Loops are the part, as I told you, GPUs are basically single instruction multiple data or single instruction multiple thread. And generally these kinds of parallelism are found in the loop. Loop is doing the same instruction, if you see, across multiple data elements. You don't add parallelism to a function, you don't add parallelism to anything else, you add parallelism to a loop, because your loop needs to split and that data needs to be divided to be run in parallel. That's why you will see this parallelism to be added just before the loop. You want the loop to run in parallel, not a function to run in parallel or anything else to run in parallel. Okay? And you can do multiple things, but one additional thing which is very much needed that you would have studied in the OpenMP side also is that sometimes you might have special kind of dependencies in your code. Like this is an example of reduction. What is reduction? Reduction is an example where you are reducing multiple values to one single value, right? Like if you want to add all of the elements in an array and store it, reduce it to one value, right? This is an example of reduction. What is the problem with reduction? In parallelism world, you are going to write to one single variable, right? In this case, you are writing it to one variable called as temp. If you run multiple threads and all the threads write to the same variable, this condition is called as what? In the parallel computing world. Sorry? Somebody said something. Data race. It's called as data race, which means you're trying, multiple threads are running in parallel, but everyone is trying to write to the same variable. When one thread is reading, another thread is writing. And this kind of creates a data race problem. Not everything can be made parallel, right? There are certain restrictions. If it's a fundamentally a sequential problem, you cannot make it parallel. But reduction is something which can be made parallel, and you don't have to worry about how it can be made parallel, but you can expose. If you have something like this where one particular variable gets written or overwritten by multiple loop, in that case you can specifically say I want to reduce, I want to do a reduction on temp variable, and the reduction is of type addition. There are different kinds of reduction. I can add all of the values, I can reduce the values, I can find max value, I can find a min value. There are different kinds of reduction operation. So you can add reduction clause to make sure that the data race goes away and you get correct results. If you don't add it, not just about GPU, any other parallel program, you will get wrong results, because that's the nature of parallel program. You have to remove dependencies. The good thing about OpenACC compiler is that it understands this and it will auto generate this reduction for you even if you forget it. It will actually tell you, I found a reduction in this loop, I will generate a reduction for you. There was a dependency I found and I am going to generate a reduction for you. So the compilers have become more and more smart over time, and they can find some of this dependency in case, in some of these clauses, in case if you use another clause, you would see that it actually throws an error telling that I cannot make this loop parallel because there is a dependency between the loops. If I make it parallel, your output is going to be wrong. So I am going to ignore your instruction and make it sequential. That's what it will do. So the compilers can give you all of those different kinds of hints. As I told you, there are different kinds of reduction, plus, star, max, min, and other bitwise operator also. To compile your code, obviously you have changed the code. The step one was to analyze your code, find out where it needs to be made parallel. Step 2 was to make that particular loops parallel. The step 3 is to parallelize, once you have parallelized your code, to compile it and run, right? To compile and run, what I told you was, for compile and running, we are going to use NVIDIA's compiler stack, or it's called as HPC SDK. So it's a free set of tools. As you can see, it has multiple things. It has different set of compilers. It has the math libraries that we were talking about. It has the communication library like OpenMPI, which understands CUDA. It has different support for different programming models like C++ and Fortran, OpenACC, OpenMP. It also does analysis. It has profilers. It has debuggers, and much more over that, it also has something called as containers, which we are not covering here. So the compiler that you are going to use in this particular session is one of this. Either you will use NV Fortran, which is for Fortran, or you will use NVC or NVC++ compiler to write OpenACC code. Now you might ask, can I use GCC or the GNU compilers? Yes, you can use GNU compilers. By default, OpenACC is not enabled inside it. You have to download a particular branch of GCC compiler to enable OpenACC inside it on the GPU. By default, it will not come. So you have to download a particular branch. But as I said, OpenACC is a specification and different compilers implement it. So the compiler that we are going to use for this session is NVIDIA compiler for making use of OpenACC. And then to the compiler we are going to give it some additional flags. There are certain flags which we are going to enable, and I am going to explain those flags to you. But to tell to the compiler that I have added OpenACC directives, and please consider them, don't ignore them, you are going to add something called as -ACC. -ACC is going to tell to the compiler that those special instructions or special comments you should consider and not ignore. What if I don't give ACC, what will happen? Your code becomes sequential, the older code, right? So your code still remains. Just by adding this flag, you are telling that now I want to convert it to multi-core or GPU, right? So that's why I meant it is incremental, your sequential code still remains. And in the end, you will also tell it a target architecture which we'll look at, right? So you will see NVCC and you're going to compile the code, and then one more important thing is you can actually provide it with different kind of architectures as I told you about. So the same code once you have written, if you tell that I want to use multi-core, I wrote the code but I have not told it what architecture to compile it for, right? So I can compile it for multi-core by telling at compilation time, compile it for multi-core, or if I have a GPU, I can tell that compile it for GPU. So based on the hardware you have, you can target different architectures also if needed using OpenACC. With GPU, you will get more performance. With multi-core, you will get lesser performance. That's the only thing, but it will run across different architectures. And I'm going to show you a very quick demo of it. But the last but the most important flag that I wanted to show to all of you is -minfo equal to Excel. I told you that OpenACC directive is a specialized comment, or it's actually something which the compiler can ignore if it wants to, right? How do you know then what compiler has done? Is via adding this flag called as -minfo equal to Excel. What it tells to the compiler is, if you are adding parallelism, please tell me what you did. So it will give you hints, like when you compile it, if you compile it with -ta equal to multi-core, which is target architecture equal to multi-core, it will tell you that at line number 63 I generated a multi-core code. At line number 74 I generated a multi-core code. If you don't see this, that means compiler has ignored your instruction because it felt it is wrong instruction, right? Or the loop cannot be even made parallel. So the same code, if you run on a multi-core, you should see certain x speed up, 3x, 4x, 8x, whatever number x based on the number of cores or the GPU or the CPU you have. Same code, I am not going to change the code, but instead of saying -ta equal to Tesla colon managed, if you see, instead of saying -ta equal to Tesla colon managed, if I say ta equal to Tesla, ta equal to multi-core, if I say -ta equal to Tesla, Tesla is the name for NVIDIA GPUs which come in the server. So it's actually referring to NVIDIA GPUs. If you say that, instead of saying it generated a multi-core code, what it is saying, it generated a Tesla code. So the same code now compiles for GPU and it will run on thousands of cores on the GPU. So that's the only change that you have to do, and what you will see is the same code which was sequential in nature. When put on multi-core, it gives you certain x speed up. When you put on GPU, it starts giving more speed up because the GPUs have more number of cores and it has a higher memory bandwidth attached to it. So your code remains same, you can keep it sequential, you can target multi-core, you can target GPU, or you can target other kinds of architectures also. And that's the part of OpenACC, the advantages of using OpenACC or directive based programming. Any question? Yeah, the same thing will work with Fortran as well, right? So instead of using hash pragma, you would use $! It is actually meant for legacy codes only. the main intention why directive based programming became really popular is because the legacy codes, some of the developers are not even there anymore. There is no documentation available. If you start writing parallel code for them, you have to understand what they have written and all of those things, right? So it becomes a nightmare for converting those large piece of codes which are millions of lines of code, right? For them, directive based programming works like a charm, because you are leaving it up to the compiler to do that analysis, and in fact it is very heavily used for Fortran 77 codes, Fortran 90 codes and all. It is the most popular thing. If you are writing from scratch, maybe you might choose some other approach, but if you have a legacy code, old code, directive based programming is the best choice. Not even standard language, because as I told you, standard language only supported Fortran 2018. What if you had a Fortran 77 code? You can't use that standard language approach. You have to use directive based approach because it targets the older generation also. Any questions? Else I am going to start showing the demo, and we'll have RTAs. Maybe if you could stand, and they will basically help you out in case you are facing any issue. Devyajyoti and Apurva, you have already met them, but they are going to help me out with in case you face any problem in writing the code. Practically, if you ask me, you have to write 3 lines of code and you have 1 hour, right? So we should all be able to do it. You will be able to run it on multi-core. You should be able to also run it on many core. So I am going to show you a demo, very quick demo on what needs to be done. Keep a note of what steps I am following, but if you are facing any issues, anyhow we'll go around and we'll try to help you out with the exercise. Okay? Any theoretical questions so far? Intel GPU or Intel CPU? Which Intel GPU? No, it doesn't run on that. No. It's currently not supported, please. Intel supports other programming models. I think the one which it supports might be OpenCL. I think it supports. I'm not sure, but you can check it. Currently it's not supported with OpenACC. But yes, it works on Intel CPUs, which is multi-core. Any other question? That would be the last thing after we are done with the hands-on part. Okay, so let me get started, and what I will do is that I'm going to, so hopefully by now all of you have access to the cluster. You have been doing hands-on part. So the first thing that all of you have to do is to copy a lab. So which is present in the Scratch common. This is the folder name. So copy it, just don't forget to put this -r. So CP is for copy, -r is recursively copy this particular lab to your home directory. Okay. So, okay. I've forgotten how to do that. Yeah. This is better? So copy the lab to your, is this fine? So copy this lab, cp-r will copy it from this directory where we have the lab to your current directory, which is your home directory. If you are facing any issue, just raise your hand, and we will have the, does help you out. Even Mandar is there, so he can also help out. So in case anybody is not able to do this, raise your hand and they will come and help you out. Okay. So once you have copied, so it is in the Scratch Common GPU Lab folder. Once you have copied to your directory, you should have a folder called a GPU_lab. You should basically get a folder called a GPU_lab. So you have to go to this folder GPU lab. Inside that you can either choose C or Fortran. You can choose one of the option. If you are a Fortran programmer, you can choose Fortran, or if you are a C programmer, you can choose C. I am going to go to C folder, and inside C there is another folder. There are multiple labs. The one that you are doing right now is lab 1. So you go to lab 1. After GPU lab, you should have C and Fortran. So you have to choose one of them. I chose C. Inside C, I am going to lab 1. How many of you have been able to copy? Can you all raise your hand? Okay, so looks like almost everybody is done. So once you are here inside lab 1, as I told you, the code that you are trying to solve is the Laplace heat transfer problem, right? So you can see here there are multiple files. So like if you see Jacobi.c, this Jacobi.c is your main function. This main function has, we are defining the grid size to be 4096 by 4096 element, and we have defined the convergence value to be 1e raised to minus 6, right? And this is the loop that I was talking about. This is your outer loop which does the checking of maximum number of iterations. Calc next is the one which does the Jacobi, the averaging, and swap is the function which swaps the element, right, a new and a element. So this is your main function, but the main place where you are going to basically run your code or change your code is Laplace2D.c. Okay, so Laplace2D.c is the function where you have different functions which has initialize. Initialize is for initializing your grid, right? So you are initializing the whole metal plate with a value of 0 or 1 based on the place. So you will only have the one value for the top, so that when you start averaging it will show your simulation. Then calc next is the one which I told you is the one which does the averaging part. And last but not the least is your swap function which swaps the new array with the old array, right? So your main functionality which exists is inside the calc next, initialize, and the swap function which you are supposed to make parallel. Okay. In order to solve certain problems for you, what we have done is we have already created a submission script for you so that you don't have to worry about submission. But I will go through the submission script for you so that you understand what we are doing. The first thing we are doing is we are trying to load a module of NVIDIA HPC SDK. I told you that you have to use a compiler, right? The compiler is present in the NVIDIA HPC SDK that we are loading. After that, we are basically compiling the code first for multi-core, and then I am going to compile the code for many-core, which is the GPU. And I am going to run this particular code. You can see here for the CPU I am asking for 4 cores, and for the GPU I am asking for only one CPU core, but I am along with that also asking for a GPU. So all of you will get one GPU to execute it. Because we have more people, I am running it through a batch script because there are limited number of GPUs and we could not give you exclusive access. So I have already written the script for you. You don't need to worry about the script. The main thing it is doing is that it is loading NVIDIA HPC SDK. You will first compile the multi-core code, you will run it, then you will compile the many core code, you will run it, and I will talk to you about the last one, which I will do later on after you are done with the first part. Okay. So again, coming back to the part, if you are in lab 1, what you are supposed to do is you are supposed to change the code Laplace 2D.C. Go to Laplace 2D.C, and what you are supposed to do, how do you make a particular loop parallel? What do you do? Hash pragma ACC parallel loop. Simple enough. So you are telling to the compiler, I want to run this loop in parallel, right? Same thing, you have another function called as calcnext. You are going to say hash pragma ACC parallel loop. There is one more for loop here, which is again here hash pragma ACC parallel loop. Right? Not so difficult. So we are trying to add parallelism to the part which is having loops. So you are adding parallelism to the loops. Before the loop you are saying hash pragma ACC parallel loop, because you want to make the loop parallel, right? You are splitting the loop, that's why you add it before the loop. Once you add this particular parallelism inside, you can come out of the code and just submit this script which I just told you, the submission script. This submission script will compile both multi-core and many-core. It will give you the timing for multi-core and it will give you the timing for many-core as well. So I am going to run this like this. So I have the submission script and I am going to just run it. Once you run it, it is going to start doing the compilation. Like it is saying me that in Laplace 2D.C at line number 37 I generated a parallel multi-core code. At line number 47 also I generated a parallel multi-core code. At line number 51 also or 62 also I generated a multi-core code. It should tell you this information. If it is not telling, that means you have done some mistake in writing that code. Okay. So once it is done with multi-core, it is going to submit a job for a multi-core, and it will, right now it is running the multi-core part. But after some time it is going to compile for GPU and run the same thing on the GPU, and you will see the timing difference in a while. It takes certain time because it is getting submitted to the job queue on the cluster, and it takes certain amount of time to compile it. Yes, that's a good question. Now, it is similar to OpenMP, and you never know, behind the scene it might use OpenMP. For you it doesn't matter. It might use pthread, it might use OpenMP, or it might use any other kind of a parallelism. It might use Intel TBB also behind the scene. Okay, so the separate OpenMP flag is in case you want to combine OpenMP with OpenACC. So you can have some part running OpenMP, you can also have some part running OpenACC. So you can add both MP as well as ACC to the same code if you like to, right? But right now we keep it simple. OpenMP is different, ACC is different. So you can see here, let me just tell you what the output is. So first it compiled it for the CPU, right? How do I know whether it compiled for the CPU? Because it said it generated multi-core code. After generation of the multi-core code, I ran the code for 1000 iterations, and it took almost how much time? 81 seconds on a multi-core machine. After that, it compiles the code for the GPU. How do I know whether it has compiled the code for GPU or not? Because it is saying generated what code? Tesla code. So it has now generated the GPU code, and after that how much is the time taken? 1 second. right? Same code, 3 lines of code, multi-core and GPU. Now this is in seconds. What if your code simulation was running in hours? So instead of 80 hours, now you can do in 1 hour and finish your PhD faster, right? That's what it means, the productivity. Don't worry about the last part. I'm going to talk about the profiling part of it, but you have to reach this stage where you are supposed to see this performance, see that it is generating multi-core code, see that it is generating the Tesla code, see that it is giving you the performance improvement. You can write it in 2 places, you can write it in 3 places, try only one place and see what happens. That's the part that the programmer has to do. If you write it in only one place or 2 places, you might not get the performance that you expect. In fact, it can reduce also. Why it can reduce is the part that I am going to show when I profile the code for you. You didn't put it in swap. It's taking a lot of time, right? Okay. So that's the part I'm going to explain. Right now, add it to both, do a control C, add it to both and see the timing. Then I will tell you what happens when you add it to only one. I will explain that part via profiling exercise. Right now, you can do control C and add to both and see the performance. Have you run it by adding to both? It gave you 1 second. It's not running. Devajyoti, can you say? It takes certain time after you submit the job because it is in the queue. So we have limited set of hardware, so it's going to take some time. Make sure that you are adding parallelism to all the loops. Okay? Don't forget to add to another. Sorry? Are you seeing all of these numbers? So you are getting 1.2 seconds, right? Yeah, so within 10 minutes you are able to get 80x speed up. Right? That's the objective, to show the powerfulness of this directive based programming, that it is easy to code and you can get so much of performance. But I'm going to go more into depth. Don't worry about that part. I'll go into more details. So the objective is so the next thing is to finish the PhD faster. OpenFOAM is a slightly different beast altogether, and maybe I can discuss about that separately, because OpenFOAM is written in a way that it is really object oriented. For access of every element, it goes via a call stack of function overloading and all. So all those kinds of applications have certain problems when you want to do this SIMD thing, single instruction multiple data, because if you want to make it parallel, you have to go via that call stack which OpenFOAM has created, and it cannot make it parallel. So adding OpenACC to OpenFOAM is a very difficult task because the code is written in this particular fashion, but there is an attempt made. You can look at something called as Rapid CFD, which is an OpenFOAM version which runs on GPU. But it does not have almost everything of OpenFOAM, but a subset of it is there in Rapid CFD. So somebody put effort to convert OpenFOAM using on GPUs. Yes, you have to. No, OpenFOAM source code is available, right? You can anytime go and change the code. People have done certain research work around it and they have parallelized it. OpenFOAM as an application is very good across MPI. It is very, very good. But when it comes to vectorization, or when it comes to this kind of a parallelism, it's not so much good in the structure. Right. We don't expect any user, unless it's your PhD thesis, to convert OpenFOAM to GPU. Should not do that. Yeah, because conversion of those kinds of application takes years of effort because it's millions of lines of code, right? You can't just make one function parallel and expect some speed up because it's spread across so many hundreds of files, so many functions. It takes time. You can look at rapid CFD and see. How many of you have been able to get the 1 second on GPU? Can you raise your hand? If you are facing issue, you can ask the mentors. They can help you out with the numbers. So I hope all of you have finished the hands-on. Is there anyone who is remaining in the queue? Queue, right? So after that there is srun command which submits the job to the queue. So they are kind of, compile is local, and once they submit it goes to the queue. That's exactly. So the time it is showing you after compilation is because you are submitting a job to the cluster, and only if the GPU is free it will allocate to you. The actual time is printed 1 second, but it takes time for you to get into the queue and access that GPU. That's why it might take time. So don't worry about that part. Once you have made it parallel, I think it should be good. So I am going to go through the part once more in terms of the code. So you don't have to worry about that. Behind the scene it will consume all the GPU cores which is available on that one GPU which is allocated to you. So it will consume all of them. By default it actually prints out that value for you. If you see, when it is compiling, it is telling you the number of threads per block, and also it gives you certain information about what is the dimension it has chosen for you. So what I have covered so far is the most fundamental thing about the computing, right? But I just wanted to show you once more the part of compilation. So we automated everything for you, but the idea is as follows. If you are writing code from scratch, the first time you are going to compile it with -ta equal to multi-core. So the first time when it compiles, it shows you for multi-core. The next time when it compiles, the same code compiles for -ta equal to Tesla colon managed, and it is showing you the information which is which line number and all, because we have added a flag called as -m info equal to Excel, right? So this is the part is what we have kind of automated. If you see behind the scene in the submission script, this is what we are trying to do. We have first loaded the module, then we are first compiling it for multi-core, and then you are submitting the job. This submission of job might take certain time, and that's why it is showing you that it is stuck somewhere, and then you run the application. Then next time you are compiling it for the GPU, and then you are running it once more, right? There was one more part which I kind of highlighted here, which is here, the last part. So I told you that there are profilers to tell you how you can identify the bottlenecks in your application, right? So one of the profiler which exists is called as NSYS or NSIGHT. So it is a profiler by NVIDIA, and when you are compiling or running your code, it will generate a file, and if you visualize it, I will be providing you the links into the Slack channel later on. You can go ahead and download this profiler, and it will give you more details inside. Here, like it is telling me that how much time is spent where. So it is telling me my application started at 0th second and it took me almost 6 seconds to finish. Okay. So if you see, this profiler is a way for you to visualize your application. It gives you information like how much was the duration of your application, and during this duration what you were doing. So it is telling me, like, this is a different example. This is not the example that you are seeing, but it is telling me there are 80 CPU cores on the machine where you are running the code, but out of which I only used 2 cores, 40th core and 0th core. So even if you are writing multi-core code, you can actually figure out which cores you ended up utilizing, and inside that course what were you doing. Like it can say the CPU utilization of core number 40 was 99%. While your CPU zeros utilization was in between, it used to come and then it never used to come, right? So it is telling you information about the CPU part of it. So what if you are doing different kinds of file IO operation? If you are doing file IO, it will also show you that you are spending time in file input output and those kinds of other things also. So it gives you over time the duration of your time, where are you spending the time in your application. And that's the most good part about it, because what happens because of that is you get more clarity in terms of where you are spending time. Along with that, this code has also run on the GPU. So you can see here it is telling me this code was run on NVIDIA Tesla V100 GPU, and if I expand on it, it tells me that most of my time was spent on the kernel, which is the hash pragma that you have written, but very less time was spent on the memory transfers. I told you that CPU and GPU memory is different, so you have to transfer the memory. Luckily in this code you didn't transfer the memory. Now you might be surprised why. That is because of the flag that you added to your code, which is so I told you that -TA equal to Tesla compiles for GPU. But there is one more flag which is called as managed. Managed is a flag which is provided. It's not part of OpenACC specification, but it is part of NVIDIA compiler. What it does, it manages the memory for you. You don't have to worry whether the memory was allocated on the CPU or on the GPU, when should I transfer it. And that's what is the advantage that you get by using the NVIDIA compiler also, because it understands and does some of these things for you. So in your code you didn't do explicit transfers, it was taken care by the compiler for you of the transfer also. So 98% of the time in kernel and 2% only in memory, and if you hover over it, you will see that it is telling me, actually zoom in, so this many times your kernel was called. These many times you can keep on zooming in, you can see here my window is changing and it will keep on giving you more information. Like I ran the Jacobi code, and that particular Jacobi kernel ran so many threads. So you can see here it ran 32 by 32 threads by 512 by 512. So many threads it has run behind the scenes for you. 512 by 512 by 32 by 32. So many threads it has run. It took around 4 milliseconds for running one of them. So that's how you can get more information about both the CPU as well as the GPU. Now sometimes if you don't write the code, what if you made only one particular loop parallel? So let me give you an example what happens. So what I am saying is that suppose you made only this particular loop parallel, which is calcnest, and you didn't make the swap function parallel. What if I forgot to add parallelism here? Can anybody tell me what will happen? This is my loop. In a loop I am calling calcnext and swap again and again till the time it converges. I made only calcnext parallel and not swap parallel. What will happen? It will make your calcnext parallel, run it very fast, but when it comes to the swap function, where is it running? CPU or GPU? CPU, but where is the memory? In the GPU or CPU? Before that you ran where? This function is where? GPU. So where is the memory? GPU. When you run on swap, where does it run? What will it do? Transfer, communication. Again it comes here. Where is the memory? CPU. Then what will it do? Copy, 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 copy will kill your overall performance. That's why when you are writing the code, the real world is not so nice, right? What we showed. In the real world you will face these kinds of problems that Sometimes your copy and everything will be higher as compared to your kernel execution because you didn't make enough parallelism and all. And those things is an iterative cycle which I talked about. Analyze, parallelize, optimize. Analyze, parallelize, optimize. The first time you write a parallel code, the performance will be worse than sequential code. Is the fact of every parallel programmer. Then you profile it, use profilers, use these kinds of profilers. It will tell you that okay, you are doing to, it will shift. If you run that code with the swap not being parallel, it will show you 98% is spent in memory and only 2% is spent in compute. It will suddenly shift and it will give you an idea that I have to make other things also parallel. So let me go there and make it parallel. So make use of these tools are very important because you might assume I made particular one function parallel, it should give me the best performance, 40x, 80x, 100x, but that's not how it works. You need to get into this cycle of APOD, analyze, parallelize, optimize, analyze, parallelize, optimize. Sometimes debug also because you will get wrong output also if you have not taken care of data races, deadlocks and all those kinds of things also, right? So my intention was to show you different methods. One of the method which we saw was OpenACC. It's very easy to use OpenACC, but it is still developer assisted programming. It will only do the job of parallelizing it, but what needs to be made parallel is your task. And for that you need to use profilers. There is no way, there is nothing called as automatic parallelization. There is a lot of research going on from past I don't know how many years, but I don't think so it will ever.
I wanted to say this in my first automatic parallelization, right? So when I started my PhD thesis work in 2003, 2004, I was working on parallelizing some sharp interface method, and I was doing all this. At that time, we did not have thing, and I was working on OpenMP and MPI. And my advisor came to me and said, why are you spending so much effort in trying to parallelize this? Here is this expensive compiler. It was from PGI, by the way. And they said that it has automatic parallelization. You just you don't have code MPI or OpenMP yourself, and you just put a compiler flag automatic parallelize and you'll get speed up. I told okay, if you are ready to buy that compiler, PGI at that time was a commercial compiler, so you had to actually buy it. So I said you buy it, and it cost I think about $2,000 or $3,000 back then, and he bought it. And then I compiled my code, and it ran twice as slow. So any of this automatic parallelization, right? Because the algorithm is finally your algorithm. You have to really tune it, and unless you get down to the lower level and parallelize it yourself, it's just going to be a disaster. And I think decades later, we're still there. Automatization is not possible. That's a comment. Thanks.
Yeah, after some time when you start giving these lectures here after your PhD, you will say the same thing. So it will continue. There won't be any automatic parallelization, at least in the near future that we see. So yeah, so it comes back to the first slide that I said that when the hardware changes, the software changes. If you don't add parallelism, you're wasting the resources of that particular hardware. No matter how big a hardware or supercomputer you buy, if you're not made it parallel, you're wasting those resources, right? So any questions on this part, because I wanted to then spend certain amount of time on the last topic. So there are more labs which are present there. We'll be posting all of these labs onto the Slack channel. You can go ahead, download it. You can try the other labs also. Because what we have touched is just the surface of what you can do with OpenACC. You can do optimization, you can take control of data transfers and all, which is part of lab 2 and lab 3. So if you want, you can later on go ahead and also download it. We'll be giving all of these source codes to you and the presentation, so no worry about that. But any questions on the topics that we have covered so far? If not, then I'm going to shift the gear in terms of a particular topic which I said we'll touch upon was the part of AI, but I just wanted to define it in a particular way, what it means, right? So what we have been traditionally taught is to take a particular mathematical equation or whatever is the software, or whatever is the maybe sorting or FFT or whatever it is, give it to a programmer, the theory. The programmer takes it, takes the task, takes the expert knowledge who have defined that algorithm, and then convert it to a human readable form which you execute. So any human, like if I write a code, you can read it hopefully. If I write it in a good way, you should be able to read it and understand what it's doing. That's like software 1.0, which is like once I write it, I can give it new input data. I've already given the logic, I've created the logic, and output is the output data. Like input data could be unsorted data, my logic is say merge sort, and the output is basically your sorted data. Software 2.0 is a reverse engineering approach where instead of you writing that logic, you provide it with tons of examples, and the output that you get is a machine learned function. It's not human readable, it is machine learned function, also called as reverse engineering, and that's what is being called as is the software 2.0 approach, where you can see instead of input, logic and output, it is a reverse thing. You give it a lot of examples, input and output, and the output that you get is the logic itself. Now there are various scenarios under which it is used. Maybe one example of it is, it's a different way of building software. So like you gave it an input of temperature, pressure, moisture, and then you have a set of functions which does the probability of rain. Now one option of handwritten function is, I already have a lot of mathematical foundations, I convert it into a human readable form, I write equations, physics equation on updating the mass, macrophysics or whatever it is. While the machine learned approach is slightly different, where it consists of set of mathematical functions, but along with that it has certain weights. You can see here that it has certain weights which are initialized to some random values, and the idea is by the lot of input and output examples, it tries to optimize these weights in a way that they start behaving like your equations. That's the goal basically. So they start behaving, or they start solving the same things which otherwise you have written or hard coded, and that's why this approach is also referred to as reverse engineering approach. Now why do you use it? There are various reasons for using it. There may be human expertise which is present. Maybe we don't know even the algorithm behind it. We know the phenomenon what is happening, but we don't know how to even explain it. There are certain places where we can't explain our expertise. It's very easy for us to write certain algorithms or equations, but there are certain things which we cannot write. It's very difficult. Me speaking in an English tone which is slightly different from the way you speak, right? Or different dialects, speech. So let's take an example of this image. Now if this image is there, it's very easy for a human eye to look at it and say that there is atmospheric river inside it, because I can look at a pattern which is coming out inside it. Can you write an algorithm which can find this in this image? How will you write it? It's a very complicated algorithm to find which pixel and what patterns are coming and all, right? What if I tilted this image? What if there was certain amount of patches which were there from the satellite imagery? Right? The amount of permutations and combinations which come there is humongous, right? So there are certain things which is very difficult for us to, like one of the biggest example is speech recognition. So if I am speaking and if I want to do this translation from one to the other, or if you want to understand from convert it into a text or whatever, there are very few algorithms, and there are no algorithms which cannot be used without artificial intelligence. The only way to use this speech recognition and everything is using AI, because it's very difficult for a human to write that algorithm. The number of the languages, the dialects within it, the different things which come into the picture, it's almost impossible to do that, right? That's where I would say that the example of artificial intelligence is there, but if I were to summarize the part of what it is, I can just say simply that AI or deep learning is nothing but an example of generalization of a curve fitting problem. Generalization of a high dimensional curve fitting problem. That's it, that's what it does. What it does is, you have a set of input data, it tries to fit that curve. It is trying to find those weights which I just talked to you about here, by it tries to change those weights in a way and tries to find those values in a way that it is able to understand the pattern in your input data set. That's what it does. So it's a generalization of a high dimensional curve fitting problem. It's iterative in nature, and you have different kinds of optimizers which tries to do this curve fitting. You don't do it for 5 feature set or 8 feature set, you do it for millions and trillions of feature sets. Not a small problem, a large problem that needs to be solved. And that's what it does, right? So it's a generalization of a very high dimensional curve fitting problem, and there are different techniques and all to do that. I am not going to go into that part, but let me cover the part which is very interesting, which is the challenges to the part. One of the most difficult part about the neural networks is that I said it's a machine learned function. How do I know whether it is actually solving the physics equations? Can I guarantee it will always work in all the conditions? Can I guarantee different kinds of uncertainties which rise, right? So that is the part. So neural networks are popular, but the scientist community is still not ready to basically adopt or use these techniques at this point of time, right? So the concept is simple, that you have your input, you generally have the mathematical model of first principles, and you're getting the output. That's what has been written by the domain and the scientist. But a programmer takes that knowledge, does certain level of approximation, because you cannot exactly represent some of these mathematical equations in the computer, right? And then you have your output. The question that the community at this point of trying to solve is this: can this approximation strategy be neural networks? Can I use optimizers to do that high dimensional curve fitting and try to figure out these equations rather than me writing it on our own? Can this work? Absolutely yes, because there is an algorithm which states, which is called as universal approximation theorem, and it is very simply states that no matter how complicated the signal is, it can be represented by a neural network. That's what it states, and it is already proven that it can do this. But it is practically a useless theorem unless you prove it for your domain, right? You can represent any signal, but if it is not able to do or learn the equations on that particular data, it's of no use, right? So the scientific community is trying to figure out this part, that what is that subset in which the neural network is going to work. And for that particular part, I am going to talk to you about one new techniques, which is the most promising technique which is happening in phase at this point of time. To solve some of these challenges which the scientific community is asking. Can I understand what the neural network is learning? It can learn. I know it works for certain scenarios in CFD also, but how do I know what it is learning? Can I prove it? Which means I am trying to do the reverse engineering that the neural network did reverse engineering on. So I am trying to see if it has actually solved that equation. Will it always give me right answers? Can I actually always trust it? How much training data do I need for doing it? Can I be always certain of the data? So there are different approaches in the scientific community that can be taken. One is the art approach, which we just talked about, where I just assume that whatever neural network is learning, whatever those black boxes learn, it's good enough for me, and I just go ahead with it. But that's not what the scientific community wants. The scientific community is going more towards this direction, which is what is called as physics informed neural network. So there are neural networks which are being devised, and if you see the neural network, what you do is basically the neural network tries to learn, but how do you measure whether the neural network is good or not? By a loss function. So the loss function is defined in terms of your physics equations. So your loss function is actually your physics equations which you add it to the end, and if your loss is very low, that means your neural network is actually learning what you would have actually meant it to do. So you cannot solve all the problem, but since your loss is too low, it's like the previous place also, right? You converge till the time the loss was, you reach the convergence state. Same thing you do to the neural network. Your loss functions are your equations, you add your boundary conditions to it, it tries to identify, and if my loss is too low, that means indirectly I am saying that my neural network has actually learned the things. And in order to do that, now this name is changed, but let me just, the name is renamed to modulus, it's no more called as SimNet, but it is basically a collection of different things in the artificial intelligence space, where you have different set of solvers, differential equations and neural network exposed in a way that instead of using your traditional approach, you can now use neural networks to solve the same problem. You can define your geometry, you can define the voxels, you can define it, the boundary conditions and everything inside it. You can write your own differential equations using Python, and you can define your loss function, and you choose your optimizer, and in the end the output that you will get is a neural network which can do this. Now the question you might ask is, why do I need to do this? You can do this because neural networks are proven, once trained, to be not 5x, 10x faster, they can give you 10,000x faster also. Because once they are trained, they are very, very fast. So you get speed up numbers which are amazing. Rather than taking days, you can finish that same thing in seconds. And that's the promise that neural networks bring in once you have trained your network. So this is the new thing which is touching almost every domain, whether it is CFD, molecular dynamics and all, does not matter. But there is research work which is going on where I try out my traditional approach, but also I try to create a neural network using physics informed approach and see if both of them are giving the same results. If they are giving the same results, you will see that the neural network is much faster as compared to. So the new approach or the parallelism or going faster is not about writing parallel code, but it is also about changing the way you write codes. It is changing the approach. Here you are not writing codes in a traditional way, you are using the neural network way, which is much faster as compared to writing your traditional simulations that you write. So if you are working in this field, we will highly recommend you to look at physics informed neural network as one of the approaches to solve some of this task. Can't say that it is in production. NVIDIA uses in production to design our own servers. So NVIDIA have their own servers and we use it for different kinds of simulations using neural network to design our own servers. So it's used in production. We are not just talking about research here. So it's something which is already there and it is going to touch almost every field. Sorry?
Is it audible? Yeah, because actually you are saying that NVIDIA does the uses this technique because you will be having all the data based on the past record, and basically it must be analyzing those data and then maybe recording that. Is that way?
No. So there are two things which I forgot. First thing is physics informed neural network falls in this regime of unsupervised learning. So you don't need to provide any data. So it doesn't need to have any data. So it's in unsupervised form where you don't have to give it input output data. Second thing is even if you are using the other approach, not the physics informed, the traditional data driven approach where you need input and output data, I think all of us, not me, as in there are simulations which are happening from past 40 years. That output is actually your input data. So anyone who is running simulation is generating the data. And all that data is available, right, to every scientist already. It's not something that we are generating.
That's what you are saying is, I know what happens with T1, I know what happens with T2, I know what happens with T3. Am I audible?
To me, yes, but not there maybe.
Yeah, it's like I know the output for say certain cases T1, T2, T3. The computer takes this and then it sort of interpolates between T1 and T2, T2 and T3, right?
It's not doing any interpolation.
I mean, it takes number of cases, it takes a lot of data,
Yes.
and it takes a set of data, and obviously we are not asking it to come up with a result for a
That data.
for an element of the set.
Right.
We want result for something that is related to the set but not exactly constitutes the set.
Right.
So it is sort of interpolation,
Uh,
weighted interpolation.
So it's like this, right? So garbage in, garbage out. So if I gave it so far only cats and dogs, and later on if I give it camel, it will not be able to identify it.
Now what I am saying is I am giving it stuff which is related.
If it is related within that subset, yes, it
Yeah,
will be.
that's what I am saying. I am giving it what's the value of velocity at point 1, what's the velocity of at point 2, at point 3,
yeah.
and then I am asking it velocity at point 1, point 2, or somewhere in the middle.
Yeah. So basically, if it has found the right equations inside, that means it will work
It's like
for
curve
any-
fitting, as you said, it's like curve fitting.
Yes, yes, yeah. But that approach that I am saying is primarily, there are two approaches in this, right? One is data driven approach, another is the physics informed approach. In the data driven, you have to give it all that set, input sets, which falls in this regime of supervised learning, where you can give it as much as data as possible, which is required for it to be trained, and the better data you give, the better output you will always get, right? The physics informed network does not require any data to be given. It learns in an iterative fashion. The only constraint is you have to define your, in the end, the loss functions, which is the one that you wanted to reduce the error for. So it does not even require any kind of input data.
All right.
Right.
There is one more analogy I have. It pertains to law. Any case which goes to the law courts where there isn't a ruling available, they go by precedents. They go by number of precedences, and then they sort of work on that basis. So also the human mind does that.
Right. Actually, this AI has taken his analogy from there only, right? As in,
yeah, and
the
also
way we learn.
And subconsciously, if I go to my home and I have to go up 3 steps on the staircase, right? So if I change my home, my mind has that in the back. So I tend to go on a step 1, 2. This new home may have 2, but I go by the 3rd step also.
Right. Okay. So learning from experience, yeah. Yeah. Yes. They are unsupervised. As in, I am not saying in general for everything, but physics informed neural network are by principle unsupervised. We don't need to give it so many samples of input and output which are tagged. No, that's not the idea. So unsupervised learning doesn't need it, right? In unsupervised learning, you don't need to give it tagged data, and that's how physics informed neural networks are.
But neural networks, by nature, they want more and more, for a certain input, this is the output, and
Neural networks, there is a large, the highest, the newer networks which are coming out like GANs and all, they're all unsupervised in nature. Because one of the biggest problem that the community is also facing is you might not have the data that you want, right? Or you cannot basically talk about, you cannot guarantee that the whole data is present, right? All different set is present. In that case, unsupervised learning performs much more better. It has its own challenges, I am not denying that fact, but like there is a large amount of newer networks which are emerging, the new whole field is unsupervised learning. It cannot be said that unsupervised learning is not performing as good as neural network, the supervised learning. Both of them are neural networks, but unsupervised one performs really well under the scenarios where you don't have enough amount of data or when you have challenges like this that we were talking about.
So is it like this physics informed unsupervised completely, or even with a sparse data?
Combine it also. So you can combine it and make it data plus unsupervised also. There are methods to do that. There are networks like that you can develop to do that also. There is a different set of beasts which are coming out like FNOs, which is like fast Fourier neural operators. There are so many different beasts which are coming out here, which is doing certain kinds of these combinations also. So you can provide it, certain part of your network can be data driven, certain part can be unsupervised.
Okay.
Compete with other numerical methods. See, there are two phases to artificial intelligence when you do it. The first one is the training phase. In the training time, it takes a long time for it to understand those weights and all, which will take a very long duration. Once you have trained it, the idea is it actually runs it very fast, and it should give you the same results as you were traditionally trying to solve those equations. So from a performance perspective, it gives a lot of performance as compared to running your traditional simulation. But from accuracy perspective is the world of research which everybody is trying to prove that it actually gives the same accuracy. I can't say in general that for everyone it's going to give the same accuracy for every kind of differential equations that you're going to use or any kind of equations.
What kind of equation or what kind of
You can define any kind of differential equation inside it. We have already given various PDEs, ODEs and all inside it.
Sir, one more question. Sir, can we solve integral, I mean some sort of fractional differential equation with the help of this SimNet?
You can practically write any kind of equation. So we, in fact, in IIT Bombay itself, we have a particular project on this part where we are trying to solve this thing that you are just saying. So you can practically write any kind of a differential equation inside it, try to solve it, but whether it is accurate enough or not is the active work of research which I am saying. Again, I am saying that some of this is proven, but 90% of it is still the phase where the researchers are trying to prove it, whether it works for all those different kinds of boundary conditions or not. So all of those things is something that is this is a SDK. This is a software development kit. You can define your own equations, you can define your own geometries and everything and try to see if it is doing a good job or not. Right?
Thank you.
It's an extensible framework. You can define your own equations also. But this is all in Python. This everything is in Python. This is not UC or Fortran. I think we have extended the time by 15 minutes. So hopefully all of you, you got an overview of some part that we were talking about, OpenACC, GPU, but I just didn't want to talk about that part. I think you should also look at touching some of these aspects of physics informed neural network to see if it applies to your domain and try to prove. This is, again I am saying, this is the most active research, proven for certain things, but still to be proven for many of those other topics. So we are done with this session now.
Yeah, I think we are ready for our last tea break of the workshop. So let us thank Bharat once. And thanks Bharat for taking your valuable time and coming to our workshop.
Yes.
So please ready outside, please come.